Hello? 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 Works. So what we primarily does is first we did an empirical study, extracted so before our work. Great. Very honored to be the first one to present. So today I'm going to present my proposal, a multi-layered dynamic security framework for DeFi smart contract. So I'm Zhiyang Chen, third-year PhD student at University of Toronto. First, I need to introduce some background. What is a smart contract? A smart contract is a self-executing program on top of blockchain, and users and contracts can interact with a smart contract by issuing transactions. And once deployed, the code of a smart contract is immutable, and a contract accumulates a history of transactions. The transaction history records all the past executions, and they're all publicly available on the blockchain. So one of the most successful applications of the smart contract is decentralized finance, DeFi. For example, yield earning protocols in DeFi can automatically distribute users' tokens to other DeFi protocols to maximize the users' returns or interest, but they need information such as Oracle prices from off-chain from external smart contract. And one very unique property of smart contract is composability. So DeFi smart contracts work like Legos. For example, in DeFi protocol A, consisting of 4 smart contracts. These contracts are built on top of some other smart contracts, such as Oracles or other DeFi protocols, and these other DeFi smart contracts serve as the infrastructure of the DeFi and allow anyone to build on top of this. In today's blockchain industry, the life cycle of a smart contract typically looks like the following. First, developers implement the smart contract. They send it to a security auditing company, which runs a variety of tools in academia and or industry, static analyzer, symbolic execution engines, or fuzzing tools to detect vulnerabilities. They report the high-risk vulnerabilities back to the developers, and if there's no other critical issues or all the vulnerabilities has been addressed, the developers will continue to deploy the contract on-chain. And from that point onwards, it becomes immutable. The smart contract may function well for some time until one day it got hacked. In such cases, maintainers can do some emergency stop, such as trying to send a transaction to pause the protocol before the attacker's transaction hits the blockchain, but if that fails, which is very common, the funds are stolen, and there's nothing more can be done after the hack transaction are finalized on-chain. So if you look at this life cycle, the current model relies almost entirely on pre-deployment auditing. If a vulnerability slips through the auditing and no white hack discovers the vulnerability before the hacker, then it's effectively game over. So my proposal here aims to add an orthogonal defense layer that complements the existing lifecycle to protecting smart contracts from its deployment to its exploitation. So the intuition behind this proposal is what we observe. The usage of DeFi protocols can be very different for benign transactions and hack transactions. Let me give you an example to illustrate that idea. So for instance, consider a very simple benign deposit transaction. A user deposited 1,000 tokens into DeFi protocol A, which then deposited these tokens into some other protocols. And that's it for a very simple deposit. For withdrawal, after some time, the user requests to withdraw their tokens. DeFi protocol A retrieves these tokens from its underlying other DeFi protocols, queries an Oracle, and to track the current price of user deposit, and finds that the user's original deposit has accrued some interest. Consequently, the user receives 1,025 tokens, which is the original deposit plus some interest. However, what will a hack transaction look like? It looks like very differently. For example, in an Oracle manipulation attack, in one transaction, a hacker can deposit 1 billion tokens into DeFi protocol A. DeFi protocol A, as before, deposited this 1 billion token into some other protocols. And the attacker then manipulates the Oracle smart contract by donating a lot of tokens to inflating the prices of the tokens inside that Oracle. Then the hacker attempts to withdraw it from the DeFi protocol A, As usual, the DeFi protocol A withdraws tokens from its underlying DeFi protocols, but this time, due to the inflated price of the oracle, it wrongly calculates the token amounts. Now the user can withdraw 2 billion tokens back. Consequently, the attacker is allowed to get back 2 billion tokens. This is clearly malicious and significantly different from the benign transactions, both in terms of the scale of the numbers, but also the action sequence. So the bottom line here is the DeFi protocol A cannot fully trust its users. It cannot fully trust other DeFi protocols or oracles. Despite the lack of the complete trust, DeFi protocol A must still rely on them because they represent the fundamental infrastructure of the DeFi ecosystem. So building without using this infrastructure DeFi Legos would require an impractical amount of engineering work to rebuild the whole DeFi world, which is not possible. So a practical approach here is to mitigate this issue by safeguarding smart contract with these safety guards. These safety guards are inserted in the source code of DeFi protocol A, trying to guard DeFi protocol A against all the unreliable external dependencies. It can, including the users, oracles, and other DeFi protocols. Additionally, it involves performing internal health checks for each transaction to ensure the protocol remains in its healthy state. In practice, these checks are implemented using the guards assertions inside the code. But wait a second, you just mentioned the after deployment, the smart contracts are immutable. How could you still instrument those safety guards? Yes, but there's a new design named upgradable smart contracts, which separates the storage state of a smart contract from its implementation logic. So in that case, it allows the proxy contract stores the storage slot, while the implementation contracts have the logic, which can be changed by updating the address of the implementation smart contract. All right, with that new design, here we propose our first layer of defense, which is how to instrument one single smart contract with runtime invariant guards for preventing the hacks. So these guards check safety properties during execution and will revert the transaction when the property is violated. To further illustrate the significant difference between a benign transaction and a malicious transaction with respect to one single smart contract, let's look at a real-world example here, the Harvest Finance hack. We collected all the transaction history data from the Harvest smart contract and measured them in terms of the access frequency, the token flow, gas consumption, and values of special parameters. We find the last data point, which represents the hack transaction, consistently stands out as an outlier in the entire transaction history, highlighting the significant difference between a malicious transaction and a benign one. With this big difference, can we do something to stop the hack? Actually, the developers are already starting to do it. So in a smart contract programming language such as Solidity, developers can actually insert the assertions statement into the code to check the contract state on the fly. However, before this work, there was no research of which invariants are most effective against known DeFi hacks, and how to choose the parameters inside the invariant is also not systematically investigated. So we conducted a qualitative study on the audit reports and source code of 63 audited projects from consensus from 2020 to 2023, and we collected over 2,000 invariants and categorized over 800 invariants into 8 categories. We find the 4 categories: access control, time lock, money flow, and data flow actually covers 94% of the all invariants categorized. Next, we are going to introduce the selected smart contract invariants in the money flow and data flow categories to give a brief overview of how it works in reality. So first one is money flow category. This one is called the token amount upper bound. This is actually very simple. It basically limits the amount of tokens that can be withdrawn in one single transaction. Every time a withdrawal is attempted, it ensures that the amount withdrawal does not exceed a predefined bound. And for the data flow invariant, it's an extension of the money flow invariant. The amount of tokens a user can withdraw is actually calculated based on several values, including function return values and some bookkeeping data inside the smart contract. The data flow invariant sets an upper limit on each of these values used to calculate the withdrawal amount, ensuring the withdrawal remain within the safe bounds. We implemented a tool called trace to inf, aimed to infer the invariant from transaction history and concretize the undetermined parameters within the invariant template. Here is our framework and an illustration of our tool. Given a historical transaction, which is a list of the opcode, we crowd the raw trace of it, and then we extract its invocation tree from the raw opcode trace. And from this, using these execution trace snippets, we apply different techniques depending on the type of invariant, such as invocation tree analysis, type inference, or dynamic tint analysis. To extract invariant-related data, each invariant type requires different data extraction methods, and we also deploy different heuristics to determine the parameter within this template. Ultimately, we obtain all the applicable invariants for each function, and we apply this invariant as safety guards to test it against the hacks which already happened. And here is the effectiveness for our tool. We find the trace to inf and these practical invariants are actually very effective. The 4 most effective invariants can already prevent more than 85% of the hacks, with introducing a very low false positive rate. And if we combine them with conjunction and disjunction, they can even have a lower false positive rate with a higher true positive rate. We also compare it with the state-of-the-art invariant mining tools or the state-of-the-art attack detection tools, and we surpass their performance both. Okay, next, let's move on to the next line of defenses in our system. So if you look at the first layer, it has a very big drawback. It needs transaction history to learn the undefined parameters inside the invariant templates, which means it cannot be deployed immediately after the deployment of the smart contract. So here's a question. Can we find a better way to safeguard the smart contract right at its deployment? What if we can instrument a smart contract only once at the deployment and have that instrumentation protected from the beginning to the end of its execution? You may wonder whether it's possible. Let's see if it is. We begin by examining control flows. Here's a surprising empirical finding. In most DeFi protocols, the vast majority of the transaction has trivial control flows. In other words, the transaction invoke only one function. The user only invoke one function. Take Uniswap, one of the most widely used DeFi protocol as an example. Here in the second diagram, the orange bar represents the trivial invocation, the trivial control flow, and the blue bars represent non-trivial ones. So if we have a line up there, we can find even for Uniswap, the non-trivial control flow account for only less than 1% of all the transactions. And for other less popular protocols, the fraction is even smaller. We also conduct even very large scale on the control flow of the hacked protocols. We analyzed the 33 hacked protocols from 2020 to 2024 using Etherscan labels to identify the contracts belonging to each hacked protocols, which crowd all the transactions over 200K transactions with this of this target contracts and extracted their control flows. A very surprising result. Out of 27 hacked protocols, 14 of them has one single hacked transaction that introduces the only non-trivial control flow observed in the entire protocols, which means if we only allow users to invoke one function in one transaction, then we could already prevented 14 out of 27 hacks. It's more than the half with 0 false positive rate. The only experienced user of the protocol is a hacker, which is very interesting. And how can we enforce such a policy? Let me illustrate a simple example involving the previous illustrative example I used. The withdrawal function, in a benign transaction, the user calls the upper level contract, which in turn invokes a guard contract here. So when a user invokes a withdrawal function, at the start and the end of its execution, it's going to report the control flow to another smart contract, which is a guard contract. And it records, okay, now the control flow is withdraw start and withdraw end. It is one simple invocation, which is trivial, and we allow it. And for a hack transaction, the hacker first calls the deposit function, and it will be recorded as the deposit start and deposit end as a control flow inside the guard contract. At this point, it works. It's still allowed. It's a trivial control flow. Then the hacker can manipulate an external oracle, which triggers which is certainly external, and the DeFi protocol A cannot be aware of this. Finally, the hacker call withdraw. Again, the DeFi protocol A will register the function call inside the guard protocol, the guard smart contract. Now the recorded control flow becomes deposit start, deposit end, withdraw start, and withdraw end, which is a non-trivial control flow, which means the control flow of that transaction actually deposits tokens and withdraw tokens in one single transaction, which is really abnormal. At this point, the guard contract can find, okay, this is a non-trivial control flow which we do not allow. Then the guard contract can immediately revert the transaction. But here also comes two main challenges of applying this system. The first one is false positives. Despite it may work perfectly well for some protocols, unavoidably we will meet some false positives, which means the transactions which are completely benign, but we revert it because we detect the non-trivial control flows. So here we introduce two policies to further reduce the false positive rate, which is runtime read only and restore on exit. So these two are two flags we track on the fly to record the properties of the execution. So for runtime read only, whenever we encounter an opcode which will alter the blockchain state, we will mark that flag as false. For restore on exit, we record, we store the storage slot that got changed and see if it's at the end going to be reset back to its original value. In that case, we do not make it a non-runtime read only. A second challenge we encounter is a very potential high gas overhead. To reduce costs, we propose several optimizations, and the most effective one being the guard contract merging. So instead of deploying a separate guard contract, we can merge it with the most frequently used contract, converting all external calls to internal ones, dramatically reducing the gas usage. If we cannot identify which contract is used the most often, we can use the contract with the largest binary size, because the more implementation logic usually means the more usage. The results are actually very encouraging. Even without training data as trace to inf, our cross-guard system can successfully stop 35 out of 37 hacks. One trained with historical transaction data in a similar setting as trace-to-inf, they can whitelist the non-benign control flows. We further reduce the faulty rate to just 0.15%. Finally, I'm going to propose the third line of defense. This is future work. We haven't done it, but we envision a systematic DeFi risk analysis framework that can continuously monitor inter-protocol independency risks before it got exploited. So again, if we look back to this graph, we find actually there are a few high risks in the whole DeFi world. If one collapses, the others could fail like dominoes. The first one is some very basic DeFi smart contracts are upgradable. For example, the most popular stablecoin contract, USDC, is upgradable, which means if one day it got hacked, I mean, all the other smart contracts using stablecoins could collapse. And the second one, the system has, well, if there's a scenario when the system has more claims on the asset, which is the top Legos of the top Legos smart contract, then real collateral supporting them, which is bottom Legos, then the system has a systematic risk. It can collapse overnight. And the third one is the DeFi Legos depend on each other. If one Lego breaks, the other collapse like dominoes. So our proposed the third layer of the DeFi Lego is to constantly monitoring the whole ecosystem. Given a protocol A, we monitor their dependencies and also monitor the overall the basic DeFi Legos, infrastructure Legos, to see if there's a potential risk behind it. So as a summary, we propose 3 layers for a dynamic security framework for DeFi smart contract. Thank you very much. I think that's the end of my presentation. Here are the reference. Thank you. Mm-hmm. Oh, right. Okay. So read-only invocations are already benign, right? It does not change any blockchain state. And there are 2 ways to detect whether a function is read-only. First, if a developer mark it as read-only, as pure function, then sure, that's read-only. But if a developer is, for example, inexperienced, they don't mark it. So we have to detect the runtime. And our instrumentation system can detect the runtime. And also there's another case, that's for the runtime read-only. We track on the runtime, which can actually mark more function as read-only to simplify the control flows. That's for the runtime read-only. For restore on exit, there are some smart contracts work in a strange way. For example, re-entrancy guard. So it's basically a lock. At the beginning of execution, it's set as 0. It's set as 1, and at the end of execution, it sets reset back to 0, just to prevent a re-entrancy. In that case, even though it changes the blockchain state, but it's a reset back, we also consider that as a read-only. It does not alter other blockchain states. Yeah, so for the for the first layer and second layer, we can consider the maybe not very precise, but first layer as data flow and second layer as control flow. And first layer only its instrumentation inside one smart contract. And the second layer, if you think about that, it's a cross smart contract. Suppose we have multiple smart contracts, and they all record the control flow into one guard contract. That guard contract can determine whether to reverse a transaction. That's the main difference. One is the data flow, one is the control flow, and one target for one contract, and one target for the multiple contracts, the complicated interactions in one hack transaction. Yeah. All the tools you mentioned, I think they're heavily utilized during the audit before it's deployed. And my tool is one additional security layer. So even after the audit, after applying all these tools, it got deployed. We're still trying to add a new security guarantee on the fly, actually. Oh, okay. Mm-hmm. I see, I see. So one thing is, once we're auditing, we do not deploy it on-chain, which means the dependencies among the smart contracts have not been established. For example, if one smart contract relying on other smart contracts, like the stable coins, or like they themselves has dependencies, if it's not on-chain, there are a lot of details which are missing from the from the detection stage. And one thing is, after so many tools, after so many audits, we still have so many security incidents every day, which means the audit may fail, and we require some new security security framework to stop this. For the static analysis, for many tools, at least what I tried, they only work on one smart contract. If there's a dependency, interdependency among different smart contracts, they fail to detect so. Yeah. Oh, but okay, go. Mm-hmm. At the same time, at the deployment, it's deployed the same time as the smart contract. Ah, okay. Yeah, that's a good question. I think the way to answer that is developers can never imagine how hackers can use their protocols. The hackers can always use protocols in a very creative ways. So reentrancy, no one has realized the possibility of reentrancy until there's a reentrancy hack. So the hackers can always exploit some very unique control flows, which no one has anticipated. And the crossguard basically means we ban all of them. Until you show me it is benign, we ban all of them, and it works pretty well.
So there were too many good ideas there. I couldn't follow what you were doing. But the one idea I picked up on is this idea that normally in a healthy life cycle, the control flows are simple.
Exactly.
And so I didn't quite understand how you deployed this. So the idea is that you put runtime guards that say if you try to do too much control flow, revert the transaction. How do I know that that's safe to do in advance, right? Maybe I need the more complicated control flow.
Okay, so first we have a few policies to try to allow as many benign control flows as possible. We have the policies over here. Basically, I think all of them are sound. We are just to analyze the.
Right, this is all heuristic, right? And
Uh-huh.
hopefully your heuristics won't end up locking a lot of money in the contract set.
Yeah, that's a good question. So first, it's configurable. Uh, we can disable it as an administrator. So if one day, as you said, they are locked, certainly if we disable, these are just assertions, right? We can disable that. We can easily introduce a new variable which will disable all the assertions if really necessary. And it is a change to the contract. It does not touch the storage. Yeah, I just changed the logic. That's the upgradable smart contract which enable us to do. And also, there are a lot of benign usage of the DeFi smart contract, very complicated. For example, arbitrage. But to protect the most interest of the users, I think sometimes we can tolerating sacrificing some creativity for the security. And also, I mean, it's configurable, which means we can manually whitelist the control flow. If it's really such a benign usage of the protocol, we can whitelist it.
But the whole point of the smart contract is you can't change it on me, right?
Mm-hmm.
You've given me a promise that's irrevocable.
Mm-hmm.
But now you're saying, oh, actually, I'm going to give you a promise that is revocable.
Yeah, I can ban you. And well, like, okay, initially I ban everything, and if you tell me, okay, it's benign, I can allow it, and then we still do not change anything. We just, as a maintainer, as an administrator, we can configure the system.
Can you take back your allowance after you've given it, or is that irrevocable?
I think all of them are configurable. Like you whitelist some control flows. Of course, you can again blacklist those control flows as well, but it takes time. Yeah, I think, okay, the fundamental idea I think here is to understand your users. Whether your users are really someone who will just invoke one function, then it makes no sense to allow more creativity. If your users are very experienced ones, then we can gradually allow more creative control flows if we prove it's healthy for some time. Mm-hmm. Mm-hmm.
I felt that one of the big themes throughout your presentation was this idea that actually the vast majority of the functionality of smart contracts is never used for anything but attacks.
Mm-hmm.
So instead of layering on checks to basically say, oh, we'll disable this, we'll disable this, we'll disable this, do we need to think in a totally opposite direction and not be using such general languages for smart contracts in the first place and have something more primitive as a protocol? Do you think like a ground up design for that would prohibit a lot of these attacks by itself?
You mean the change of the program languages of the?
It almost wouldn't be a programming language anymore. If you're saying that all the legitimate uses of this particular protocol are only individual function calls,
Uh-huh.
now your protocol is just an enumeration of which function you're calling it rather than a real programming language.
Uh-huh.
It would be way more tricky.
Yeah, I would actually agree if we have those simple functions. I mean, for EVM, initially it's very simple. But EVM is a very simple virtual machine. So even for such simple virtual machine, we still have so many security problems. And it has suffered for over 5 years. And now it reached a state. I mean, introducing a new thing, I would only introduce more security problems, which takes another 5 years to recover.
One more follow-up.
Mm-hmm.
Two things, if I can. So following up on what Conrad's asked, I thought that was a really good idea.
Mm-hmm.
Right. So your huge discovery here is, wait, we think we want complicated control flows, but those indicate hacks
Mm-hmm,
and
mm-hmm.
paths. So we should restrict ourselves to simple control flows. Going back to your first thing, where oh, we're going to look for reentrancy, right? That's what these
Mm-hmm.
static analysis tools do. You have static analysis tools. You don't change the language, but you just have a static
Mm-hmm.
analysis tool says, oh wait, it says 2 calls in a row. We've detected that statically. Don't do that. Only run 1 call in a row. And then you would just design things differently. So a question I think you should look at is, you could use your heuristic techniques where you implement this stuff at runtime,
Mm-hmm.
or a design time technique where you just do static analysis to check the control flow. You should compare these two and see how they work out. That's a suggestion for you.
Mm-hmm. Mm-hmm. Thank you.
And then I was told we should also give suggestions for presentation, if you want to present clearly. And my suggestion
Okay.
Explain one good idea simply. So things you did not explain that I would have wanted to see are what are the data sets of programs that you worked from? What counted as a fault that you detected? What did what counted as an exploit? How did you do this? None of that methodology was covered. It's important.
Mm-hmm.
And if you just explain one idea clearly with all those details, I mean, say, and I had other good ideas, but if I get one good idea clearly from a talk, that does me much more good than lots of ideas.
Oh, I see. Yeah. Probably I should explain more on the first idea.
Thanks so much. So let's thank the speaker one last
Great.
time.
Thank you.
So next we have Omar speaking on lexical effect handler, fast by design, correct by proof.
Aspect ratio of your slides.
What's that?
What's the aspect ratio of your slides?
16:9.
Okay, great, cool.
Okay, let me try it again.
Wait, are you connecting?
Well, let me try it again.
Okay, cool.
So okay, it's up. All right.
You won't need to drag it over. Perfect.
All right.
Cool. Right, so once again we have Omar with lexical effect handler, fast by design, and correct by proof. Please.
All right. Thank you very much. Hello, everyone. My name is Colin. I'm a fourth-year PhD student from University of Waterloo. In this talk, I'll walk you through my journey of designing compilers for lexical effect handlers. In the first few slides, I'll go over the background that you need to understand this talk. Effect handlers are a powerful language feature and subsumes many control flow features such as async await, coroutine, and generator. To demonstrate the power of effect handlers, here I present a program with user-level scheduling where two threads take turns to execute. We define a global variable parked, which stores the continuation of the dormant thread while the other is running. Work is where all the computation happen. We'll look at it shortly. The main part of the program consists of launching two threads. Now let's look inside work. It consists of a single handle with expression. The handle the body does useful computation, which is not shown here, and it periodically raises yield effect to transfer control to the other thread. The handler contains the code that is executed when an effect is raised. The yield handler in particular contains a scheduling logic that's simplified to look at the essence. The yield handler takes in a parameter k, standing for the leftover computation from the program point that raised the effect. This value is called continuation or resumption. Inside the yield handler, we first load the period continuation from the global variable, then we park the current continuation. Finally, we resume the period computation. When this program runs, the two continuations take turns to execute. If you've never seen a continuation before, I hope that you find this example magical. Remember, traditionally, a scheduler like this has to be implemented by a runtime, like an operating system. Now, it can be built entirely within the programming language. Effect handler, though powerful, suffer from a modularity problem. In the next few slides, I'll walk through an example to illustrate this problem and show how recent work on lexical effect handler address this. Assuming you're an application developer, you import a plugin and framework from third-party libraries, and you invoke framework by instantiating the plugin. Now say you want to monitor the usage of plugin by the framework. You create a wrapper function that calls plugin and then raise a login effect. And you also install a login handler in your application. Now, since effect handler isn't mainstream yet and most of you don't have experience programming with it, let me explain why the programmer would expect this to work. Programmer expect this to work because both the raise and handle with expression use the name login. And because the name appear in the same lexical scope, they would expect them to refer to the same thing. And why would a PL designer want this to work? Well, we built PLs to help programmers write modular and reusable softwares. In order to be reusable, the framework should be agnostic or polymorphic to the effect of the plugin. If we indeed have such a modular PL, then the framework is statically prohibited to do anything with the logging effect of the wrapper. Only the program text that is aware of the logging effect should handle the effect, which is right here. However, many works on effect handlers use a semantic that is not modular. When an effect is raised, it is handled by the closest handler on the stack. To see how such semantics could go wrong, let's assume that the framework that you imported install a handler for its own purpose. Of course, as the application developer, you do not know that. If you run this program, the logging effect raised from plugin will be accidentally handled by the handler in the framework. This behavior makes it very difficult to reason about the program. For example, if you import a framework that does not install an enclosing logging handler, then your application will work as expected. We know that this problem is similar to the abstraction problem with dynamically scoped variables, which has fallen out of favor since 80s. From another angle, this is a problem with names. Both the application and framework use the same name, logging, for their internal purpose, but it results in a name collision when the two modules are composed. Recent work has proposed lexical effect handlers as a promising alternative. In a language with lexical handlers, the handle with expression binds a name variable. When the lexical handler is installed, the runtime generates a fresh name for this handler. This name substitutes for the name variable inside the handler body. Here's another presentation for the same expression, which highlights the stack structure. The program has two stack frames, a handler frame at the top with name 314, followed by the current redux. This slide puts lexical semantics and traditional semantics side by side. We can see that with the lexical semantics, every handler is given a globally unique name when it is installed. The traditional semantics does not have such guarantee. Prior work have also formally shown that programs built with lexical effect handlers enjoy modularity. Now, my doctoral work focused on designing and implementing efficient compilers for lexical effect handlers. We introduce a high-level language Lexa and show how to compile high-level modular effect handlers into low-level Swift stack switching. I organize this talk around 3 pieces of work. Each solves a distinct problem centered around compilation. These 3 work expand the landscape of effect handler compilation and bring out interesting trade-offs between performance and expressivity. Furthermore, all techniques used in this work are formally proved correct. Let's look at the work which we call direct Lexa first. Direct Lexa is our first attempt at efficient compilation of lexical effect handlers. We start from the simple insight that handlers do not need an extra name because they already have one, which are their stack addresses. Using stack addresses as handler names has an extra benefit. When raising to a handler, originally we need to walk the stack to locate handlers with matching names. With stack address, this time it reduced to 01. Besides finding handler, an efficient implementation of effect handler also requires capturing and resuming continuation efficiently. Lexa achieves constant time continuation operation using a technique called stack switching. In the next few slides, we will see how stacks are laid out and how they're manipulated during effect handler operations. Stack switching consists of 3 phases: enter, raise, and resume. We'll look at them one at a time. Let's first look at what happens when we enter a handle with expression. The red arrow in the stack pointer pointing to the current stack. The handler in the handle with expression is installed on the bottom of a new stack in a structure which we call handler frame, highlighted in yellow. The handler frame contains a pointer field that points to the top of the prior stack. We call this field exchanger, and you will see why shortly. After the handler is installed, the handler computation will use the new stack for storing their local variables. Let's look at what happens during a raise. The computation is currently inside 2 handlers, so you see a linked stack structure. Say that the current program point raises to handler 1. Raise requires capturing continuation, and this is done by simply exchanging the content of the exchanger and the stack pointer. After the exchange, the stack pointer points to top of the previous stack, and the original stack pointer is stored in handler 1's frame. This effectively captures continuation, which can be resumed later. Resuming the continuation similarly involves an exchange between the exchanger and the stack pointer. After the exchange, the continuation becomes linked to the stack again, and the computation resumes from the top of the last stack. We implement the aforementioned design into the Lexa compiler. The core of the compiler is a library which we call StackTrack. It includes handwritten assemblies that carry out stack switching. Overall, the Lexa compiler first compiles high-level Lexa program into C, which is combined with the StackTrack library and sent to LLVM for further optimization and code generation. We compare the performance of Lexa with other programming languages with support for effect handlers. The results show that Lexa is not only fast in absolute terms, thanks to many of our low-level optimization, it also scales extremely well due to our design which makes raise and resume all one, regardless of the shape of the stack. Next, let's talk about multi-Lexa. The example we've seen so far all use single-shot resumption. Multi-shot resumption are resumptions that are resumed multiple times and then bring extra expressive power. This slide presents a checkpointing program which takes in a program and runs it within a save and retry handler. The program can raise save effect to save its current continuation. After that, it can raise retry effect to discard the current computation and instead resume the saved continuation. Because the retry handler can be raised multiple times, the saved continuation also need to be resumed multiple times. Although multi-shot resumption offers great expressive power, direct Lexa sacrifices it in favor of efficiency. To see why direct Lexa is incompatible with multi-shot resumption, let's see how direct Lexa implementation differ from the formal semantics of lexical effect handlers. The top of slides show the reduction step according to the formal semantics of lexical effect handlers. This configuration consists of 3 handlers. The continuation consisting of handler 1 and 2 is captured and then copied. Notice that the copies of handler have the same name. Now, say that the current program point raised to handler 1. The operational semantics walk the stack and it will correctly find the handler 1 on the active stack. In contrast, when resumptions are copied in direct Lexa, copies of the same handler will have different addresses. Although the current program point has a pointer to the original copy of handler 1, this address is useless to locate the correct copy on the active stack, which now has address 3. Because of this, direct Lexa simply aborts if a resumption is resumed more than once. In multi-Lexa, we add back multi-shot resumption, yet still retaining the performance edge of direct Lexa. Our technique borrows idea from virtual memory management, and we call it virtual resumption. In multi-Lexa, stacks and handlers live in virtual memory space, and all addresses are virtual addresses. For a given address, we call the higher bits zone number, middle bits handler ID, and the lower bits stack offset. Each continuation lives in a different zone, and copies of the same handler in different continuation live at the same relative address within the zone. See the example on the right. All 3 handlers initially live in zone 0. Say that we captured a resumption consisting of handler 1 and 2 and copy the resumption and resume it. The stack diagram will look like this. A new zone is created to host the resumption, and handler with ID 1 and 2 are copied inside it. Notice that the copies of handler live in the address with the same handler ID as their original address. This enabled efficient address redirection, as we will see in the next slide. In multi-Lexa, when a program uses an address, a software-level memory management unit, SMMU, performs address translation. For instance, if a program raised to handler at address 020, control is transferred to the SSMU, which translates the address through the following steps. First, SMMU uses the current stack pointer to determine that the current zone is 1. It also uses the given handler address to determine that the target handler has ID 2. The SSMU performs a zone walk starting from zone 1. At each zone, SMMU checks if the zone contains a copy of the target handler. The check is surprisingly simple. We only need to compare the target handler ID with the ID of the first handler in the zone. If the target ID is greater or equal, which is the case here, then this zone must contain the target handler. This must seem very magical, and I agree. The reason why this simple check works relies on two important invariants. First, SNMU ensures that every stack are created with monotonically increasing handler ID. Second, the type system with lexical scoping put another structure invariant on the stack layout. I won't go into details due to the time constraints, but I'm happy to talk about it later. The check reveals that zone 1 indeed contains a handler with ID 1. Next, the SNMU modified the given address 020 to 120, where the zone number is replaced by the zone number that the zone walk ends up in. Finally, SNMU returned the translated address 120 to the program, and you can check that the handler at 120 indeed exists and is a desired handler. We implement SNMU as a library that provides an API that includes new stack, free stack, and translate address. This library is surgically integrated into the existing stack track library, which previously used libc malloc for stack allocation. With that, Laxa now support multi-shell resumptions. The last piece of work in this talk is called Zero Laxa. With Zero Laxa, we explore a very different design trade-off. When compared to the traditional handler semantics, the lexical handler semantics has a performance disadvantage in that every function needs to be explicitly received handler arguments. The passing and receiving of extra arguments impose a runtime cost even for really raised effects, such as exception. And we're concerned that even though lexical handlers have nice theoretical properties, language designers might still shy away from adopting them because of this overhead. Generation of language designers have advocated for zero overhead principle for exception handlers. This idea is best described by the quote from Bjorn Stroutrap: "What you don't use, you don't pay for." Zero Laxa is our attempt of achieving this goal, making Laxa the first language to have zero overhead lexical effect handlers. In the next few slides, I will demonstrate the technique by walking over two examples. We will first see a non-zero overhead execution, which is the state of a world now, and then we will figure out how to make the execution zero overhead. Here's the first example. I show the program on the left and a stack diagram on the right. Please only pay attention to the diagram on the right. Now, as the program runs, the function main install a handler which is given address 5. Next, it calls foo by instantiating foo's handler parameter with this handler. The black box denotes a handler parameter binder, and the arrow denotes a parameter instantiation. Inside function foo, it installs another handler, which is given address 6. It then calls bar by instantiating its two handler parameters. Finally, bar raised two handler at address 5, which transfer control to the stack at address 5. Similar things happens when bar raised two handler at address 6. Now let's ask ourselves, can we locate the intended handler without passing down addresses? The key observation is that the handler provenance, which are represented by the arrows, are known statically. Even if we don't explicitly pass down the addresses, we still have a way to know where the handler passing originates. We can just trace back the static provenance information and find the intended handler. Let's see in action how handlers are located in Zero Laxa. When an effect is raised, the control goes to a runtime stack walker. The stack walker carries a state called clue, which is a single integer denoting the de Bruijn index of the handler variable responsible for the raised effect. In this example, the clue is initialized to 0, which is the de Bruijn index of the handler parameter h2. The stack worker walks up the stack. At each call site, it transitions the clue according to how the handler parameter is instantiated. In this case, h2 was instantiated by the local handler inside foo. Since this local handler's de Bruijn index is 0, the clue is updated to 0. Finally, while still inside foo, the stack worker finds the local handler with de Bruijn index 0. It thus successfully finds the handler. Oftentimes, works about effects and handlers becomes challenging when it comes to higher order functions. However, zero laxa also works with higher order functions. Similar to the first example, this example also has three functions: main, foo, and bar. Notice that the bar is a first-class function that is defined inside the scope of two handlers. And also notice that foo is a higher order function that takes in an alpha and a g, where alpha stands for the effects of that g raises. There are two cosi in the example. At the cosi of foo, the alpha is instantiated with two handlers representing the effects the function argument bar can raise. Let's see what happens when we execute the raise expression from the function bar. We start stack walking with an initial clue infinity. We use infinity to denote the fact that the handler variable log is bound outside the scope of bar. From another perspective, log is captured by the function bar. Furthermore, the clue contains an extra field to record effect name. This extra information will be used to disambiguate a fork on the provenance path, which can already be seen on the diagram. When the stack walk arrives at the cosi bar, it replaces the alpha in the clue with 0, which is the de Bruijn index of the effect variable alpha. To see why this makes sense, remember that an infinity clue refers to a handler captured by the bar, and alpha represents exactly the set of handlers captured by the bar. So it's sound to attribute the effect to alpha now. Next, the stack worker reached the next cosi. The Bruijn index 0 indicates that effect is attributed to alpha, but alpha is instantiated with two handler variables. The second field of the clue now plays a role to disambiguate this fork. Because the variable log has a matching effect name logging, this variable is chosen, and the clue is updated to carry the Bruijn index of the log, which is 0. Finally, the stack worker finds the local handler with the Bruijn index 0 inside main, and with that, we've successfully located the target handler. Zero laxa works by compiling a source language where handler variables are passed as function arguments into a target language where each cosi is annotated with metadata. This metadata records how the handler parameters would have been instantiated. These cosi metadata entries are stored in the data segment of the binary and can be looked up using the return address of the corresponding cosi. Importantly, zero laxa doesn't require any extra code to be instrumented into the binary. The stack worker only consults the metadata when an effect is raised, so the cost is entirely off the mainline execution path. To integrate zero laxa into laxa compiler, we modify the compiler to emit the type-directed cosi metadata into the binary and implement the stack walk routine as shown by the diagram. We've now seen three different techniques for compiling laxa effect handlers, each making distinct trade-offs. Direct laxa is the most efficient, but lacks support for multi-shot resumption. Multi-laxa brings back multi-shot resumption, but introduces overhead due to pointer redirection. Zero laxa eliminates overhead for having the handler in a lexical scope, adhering the zero overhead principle, but raising the effect becomes more expensive. Furthermore, all techniques are formally proved correct, and you can find more details in the paper. In conclusion, I've represented three pieces of our work that hopefully will make lexical effect handlers more attractive to both language designers and compiler writers. I hope future languages will see lexical effect handlers as a compelling choice for control operators, and hopefully help reinforce a future of modular and performance software. Thank you, everyone. Thank you. Right, so as I said before, we're making trade-off between performance and expressivity, all right? Direct laxa doesn't support multi-shot resumption, so it loses expressivity.
It doesn't support
multi-shot resumption. It doesn't allow resuming continuation.
Does zero laxa support multi-shot resumption?
Yes, it does support that. I mean, so there's a trade-off. Multi-laxa and zero laxa, they all do stack walking, all right? And because of that, it's able to locate a recent copy of a handler. In contrast, direct Alexa use addresses, so they could go stale. But if they're still fresh, it's really efficient to reach the handler.
So that was actually going to be my follow-up question. How do you make sure when you are checking an address that comes to you from DirectX that it hasn't gone stale or been smuggled out of the current stacking somewhere?
Right, so the Alexa compiler supports user annotation of the handler behavior. So for example, a programmer can say that this handler capture continuation that can be used multiple times. And we will use the multi-Alexa to compile this particular piece of code. But if the programmer do the wrong annotation, well, it could be the future work, but we could have a type system that statically detect whether the usage of continuation is used correctly.
So if I'm understanding, the point is if you annotate a configuration of a handle and arrays and so on as saying, I'm going to use direct Alexa as this, you would get undefined behavior if you use it in a way where it's being leaked and used it in inappropriate places. Is that the point?
Well, it's not really undefined behavior. We will just abort the computation if we detect that you used a continuation that supposedly should be used one time.
My question is, how do you detect that?
Well, it's okay. We basically have a distinct heap cell that store a reference to the continuation, and if it's used, then we just make sure that the reference is 0. And then if we resume that continuation again and see it's 0, well, we just abort it.
So there's an extra indirection you have to go through to actually get to the continuation.
Yes.
That's what gets.
Yes.
Okay,
Mm-hmm.
Okay, anyone else have any questions or follow-ups?
I do. So, Zero Alexa, if you give it something that doesn't use handlers at all, it'll be very fast.
Yes.
What about direct Alexa?
Direct Alexa, there's a trade-off in that the direct Alexa pass down the addresses, right? So even
if that's something that doesn't use handlers at all, Zero Alexa will be faster than direct Alexa.
exactly right.
I presume you showed us a very nice evaluation graph, but only for the first method. I presume you have such nice ones for the other two.
Yeah, due to the time constraints, I'm not showing them. But the interesting example of Zero Alexa is that we have a case study where we adjust the time slice allocated to a scheduling program, right? So we can say how often the thread yield. And we observe that if we yield more frequently, then there is a performance edge for direct Alexa because you're using more frequent effects. But if we yield very infrequently, then we start to see a benefit of Zero Alexa.
So are we moving towards a perfect world where you use the Zero Alexa techniques in spaces that don't use the handlers, and the direct Alexa techniques in things that use single shot handlers, which is a useful name, by the way, that you didn't use, multi-shot versus single shot, and then use maybe multi-Alexa techniques for where there are multiple handlers. Do you think we can move towards a world where we get the best of all worlds, or are we necessarily going to have these trade-offs?
Well, I think we will have these trade-offs, but still, Alexa compiler supports compiling a single program using mismatch these techniques. So, you know, it's depending on whether, I mean, we could ask programmers to annotate, or we could have runtime detection, or we can have different techniques to put on these annotations. So the programmer's input we might not need much programmers input to make this like ideal world possible. Does that make sense? Like.
No, I didn't quite follow that. You're saying, no, I'm not going to promise we can get there, or I think we can get there.
Okay, I think we can get there. So now the only problem now is that we need annotation, and I'm saying that maybe we don't need annotation, and if we don't need annotation, then it's perfect world. All right, like you give it a piece of code, and it just automatically figure out how to best compile each handler, and you know, you get the perfect world now.
I want to give you just a little bit of feedback on presentation. First of all, it was quite clear. I could follow notes. I thought this was a great presentation. Two suggestions to make it better. One is basically just make it easy to compare things. So you had 3 or 4 different examples. Have a single running example that works for everything. That's hard to work out. It's a lot of work, but it'll pay off in that your audience finds it easier to follow.
Mm-hmm.
And the other is you have these great performance graphs for one. Have them for all 3. Figure out what else to
Sounds good. Thank you very much.
I think this is a very interesting work. I really like this kind of things. I'm just curious, what is the research roadmap afterwards?
So I am now more interested in a surface level language, because what I'm talking about now are all compiler techniques, right? We figure out, given a surface language, how to compile them efficiently. But recently I've been thinking, how can programmer best express their intent about which handlers should be used, right? Like lexical effect handlers, they basically ask programmers to explicitly pass, handlers, and the intention is very clear, but it's also very verbose. But if we don't make this verbose, then we're not sure whether we're doing what the programmers actually want to do, right? So recently I've been thinking of how to make a good surface language that is performant using these techniques, but still achieve the semantics that the programmer actually want.
Yeah, I think it would be interesting to teach language model, right? How to use them in the right context.
Mm-hmm.
Be more useful.
Yes, but still, regardless of the surface language, these techniques can be applied to general context.
Okay, thank you.
Thank you.
For clarification, is your idea that you want the source language to be less verbose? You somehow want to figure out clear intent, but in a different way without having the programmer specify it?
Yeah, prior work have these desugaring paths that you write in a traditional language where you don't explicitly pass, and it kind of figured out how to thread the handlers according to how effect would have propagated. But it's very technical, but I find that unsatisfactory because in some corner cases, it doesn't work very well. Yeah.
I really liked your answer to Phil's question, because I was wondering how you would decide which compiler crib to use,
Mm-hmm.
depending on which situation you're in. So I guess some sort of type inference is what you're hoping for.
Yeah, type inference or profiling guided optimization.
One thing I didn't get during your presentation is, on the zero Lexa section, you said this is type-directed compilation.
Mm-hmm.
But I kind of missed how it was type-directed compilation.
Yeah, we kind of use that term loosely. Remember when we face some polymorphic functions, right? We need to attach the effect name to the clue, right? That's kind of the type for the effect name is kind of type for the handler, right? So that's where the type directly kind of comes from. But also, we also need to kind of track the de Bruijn index of parameters, but that may not be the type. So yeah, it's a little bit not quite correct there. Yes.
So just a suggestion for your future research.
Mm-hmm.
You said, oh, for the future, I want to make this really easy to use and look at the source language. I think that's exactly right, but it doesn't build on the strengths of what you've done. The strength of what you've done is you've got these three different techniques. So just for finishing off your PhD, if you could say, look, if you add these annotations, the language becomes a bit messy to use, but you get the best of all these worlds. And then you're going, oh, well, that's kind of complicated. But you can say to the person who says, like me, who says that, yes, but this is an intermediate step towards getting there. Now we've shown it's possible. We've got a way of combining the three, and we can use that to guide us in then designing a language that's easier to use. So maybe you first build on your strengths, show how by adding lots of annotations you can get the best of all three worlds. That's your PhD.
Mm-hmm.
And then once you graduate, if you don't move on to something else, you can then go to the very interesting problem that you described of how do we make the surface language work.
Yes, that's very great advice. Thank you very much.
Just one more follow-up. I guess a piece of advice, but before I give it, how much have you been talking to Sam Lindley, who's also this continuation?
Well, not much, but I know one of his students is here, but so I'll talk to him.
That's totally cool. I can give this advice. So my advice is I work with the WebAssembly standards body, and we're currently fighting over how to add continuations and effect handlers into the language. One of the things we're fighting about is exactly this concept. I'm sorry, now that I'm saying this, the terminology has run away from me. The concept of lexical effect handlers versus
Sounds good. Yeah, I'd like to talk afterwards.
Would be the right person to place to insert yourself into that.
Okay. Thank you.
We have 30 more seconds before we break for lunch. Now that the panel's talked for a bit, does anyone want to have a quick question or comment from the room? Then I think we've done really well. Okay, let's all thank Conwell one last time.
Thank you very much.
Hello everyone, welcome to the second session of the Doctoral Symposium. Don't worry, I knew this would happen and there's so much slack time in this session that everyone is still going to get their full speaking time. So it's going to be totally fine. Our next speaker is Amanda Hsu. She'll be presenting how to synthesize quantum circuit optimizers. Please take it away.
Thank you. Yeah, hi everyone, I'm Amanda. I'm a PhD student at UW-Madison, and today I'm going to tell you about my PhD research. So to get us started, why do we even want to do quantum computing? Well, in the 80s, Feynman introduced this idea of using quantum computers to simulate quantum mechanics, and then in the 90s, we had these breakthrough algorithms, such as Shor's algorithm for factoring numbers, and Grover's algorithms for search. And one day, we'd like to be able to do things like material discovery, probably more than factoring large numbers. But it's kind of unclear right now when we'll be able to achieve that. But nevertheless, we've been making steady progress. In the 2010s, we started to have hardware that is publicly available. And in the 2020s, we've had some error correction demonstrations to resolve some of the issues of this very noisy hardware. And so a broad question that my work aims to answer is how can automation accelerate this timeline between where we are now and to some point in the future where we can actually realize these algorithms. All right. And in particular, I explore this question by focusing on this problem on optimizing these programs. And the main reason why we need to do this is because the hardware is extremely unreliable. So a program for a quantum computer might look something like this. It's a pretty simple circuit. And the wires, the horizontal wires, represent our state, or qubits. And then these boxes and these vertical lines represent the operations that we can perform on a computer. And we call those gates. And then the way you read this diagram, which will show up later, is from left to right as time progresses. And the issue here is that each of these gates has some probability of failure. And so once enough of this builds up, when you read your results at the end, it's going to be indistinguishable from random noise. And so what a compiler might want to do, or an optimizer might want to do, is reduce the number of gates in a program so that we can reduce the noise that is introduced to our computation. And another important thing to point out here is that the longer our program runs, the longer our qubits have to stay in the state that we want them to be in, and that's something that they don't like to do. But another objective is maybe you just want to focus on reducing these 2-qubit gates because they have an order of magnitude higher failure rate. And then we also have, when we have error correction, these rotations on the z-axis by a particular angle, which are called t-gates, are going to be hard to do fault tolerantly. So our objective shifts a little bit, and we want to really focus on reducing those, and 2-qubit gates are secondary. But let's say I have a way to optimize this program, this particular one. The problem is that it's not going to be executable on every device, because it turns out that every device supports a different set of native basis gates. And we have a lot of different options in terms of hardware, and they each have their own way of implementing this idea of a qubit physically. And so they each support their own instruction set, and as physicists and engineers work on improving the hardware, they also improve the gates. And so the supported gates for a particular hardware platform can also change over time. And we'd like to not have to rewrite our compiler every time the basis gate set changes. And if we just optimize in one intermediate representation that is just one gate set, once we translate to our target one, we may be losing out on some optimizations in that gate set. So the overarching question here is, can we automatically synthesize an optimizer that is both effective and correct, as we would like all our software to be? And to break this down, I'm going to present an optimizer as these two components. One is the set of optimizations that you're allowed to perform, and then the other is the algorithm that you use to schedule the application of these optimizations. And to characterize this landscape, I'm going to be separating it into the optimizations and algorithms that are handcrafted and ones that are more generic or synthesized. So in a sense, like a generic search algorithm is synthesizing a schedule for applying these optimizations. And just to give you an idea of what a handcrafted pass might look like, it's like this very specific and rigid schedule of optimization. Great. So I'm going to present a bunch of tools here. There's like a collection of academic tools as well as industrial toolkits. But the important thing is that all this existing work touches some region of handcraftedness, which is not going to be generic. And so the question is, can we have a tool that lies completely in this synthesized region? And so that's what the first work I'll be talking about aimed to solve. And it does this by synthesizing some optimizations and doesn't really focus so much on the scheduling algorithm portion. So then there's a question of like, what is the best scheduling algorithm given these optimizations that we synthesized? And there was some follow-up work that tried answering this with reinforcement learning. But then there's another distinction here, and it's the separation between optimizations that we're able to synthesize ahead of time and then optimizations that we can synthesize while compiling a circuit. And so the next question is, if we use both of these, is the reinforcement learning still a good scheduling algorithm? And is this even a good idea to combine these in the first place? So I won't be getting into the details of this in this particular talk, but we'll see the high-level ideas. So yeah, the majority of this talk will focus on this work CASO. And the way that we do this is by synthesizing some optimizations. So what are the optimizations that we're trying to synthesize? Well, if you're familiar with classical compilers, the things that we're trying to synthesize are these things called rewrite rules. And you might be familiar with people optimizations from your introduction compiler class. And so what a rewrite rule is, very simple. It's just a pair of programs, a left-hand side and a right-hand side that you can rewrite to. And if these are equivalent, then we call that a rewrite rule. And the way that you apply these is that you can go through your program and find matches of the left-hand side and just simply substitute it with the right-hand side. And then you can optimize according to some objective. But for quantum programs, what does equivalence mean? It's very simple. The semantics of a quantum circuit, it can be represented as a unitary matrix. And if you don't know what a unitary matrix is, it's just a matrix that satisfies this definition here. And like the dimension here is going to be not great because exponential in the number of qubits. But we'll say that two circuits are equivalent just if their unitaries are exactly equivalent. And because this is an important subroutine into synthesizing these optimizations, I just want to give you an idea that this is not an easy thing to check. Even if you had access to a quantum computer, it would be difficult to do this. But all right, so what do these rewrite rules look like? We have a few different classes. The first is like the rules that help you cancel out gates. So intuitively, even if you had like a classical NOT gate, which is this X here, you would, like if you apply it twice in a row, that makes sense that that would be equivalent to the identity. It's the same case here in the quantum setting. And we have a couple other rules for other gates that also tell you when you can cancel gates. And these are good because we're directly reducing our gate count. And another way we can reduce the gate count is by merging these rotation gates that are next to each other by taking one rotation by the sum of their angles. And then lastly, an important class of rewrite rules are ones that tell you how you can move gates across one another while preserving equivalence, because this is in general not going to hold. And you need to be able to do this in order to have any hope of having interesting optimizations, because otherwise the search would be very simple because you would run out of gates to cancel at some point. Great. And I want to point out here that these rules are symbolic, like they're parameterized on these angles theta, and this equivalence holds for all values of theta. So checking equivalence is going to be tricky. And what we also want to do is be able to check this type of rule, where this S in the middle is not only symbolic, or the circuit is not only symbolic because it has thetas, but this S could be any circuit. So you can think of it, when you apply this rule, as like a wild card on some subcircuit that satisfies a simple constraint on its semantics. And this is empirically a very important rule, and in previous work, it's been formulated, just like applied as a handcrafted preprocessing phase. Great. So the synthesis problem that we're addressing here is, given some specification of the native basis gate set for a particular device and some bounds on the size of the rules that we want to synthesize, we want to output some provably correct rules. And so how might we go about this? Well, the naive algorithm would be to start off with no rules, and then just enumerate all the circuits I can possibly have given this grammar and some bounds on the size. And then once I have this set of circuits, I'm looking for pairs because a rewrite rule has a left hand and a right hand side. And then if they're equivalent, then we'll add it to our rule set. But this is problematic because, as you might expect, the size of the circuits is going to blow up very quickly, even for small values of max qubits and max size. And then this verification task is going to be hard because our circuits are symbolic. So what does it even really mean? And then all of the expensive verification task is buried in this nested loop because we're looking for pairs of circuits. So it's not looking so great. So the overview of our approach is that we're going to take a symbolic circuit. We're going to have a procedure of representing its semantics as a polynomial. And why do we want to do this? Well, because then we'll introduce this data structure that makes it very easy to group polynomials into equivalence classes. And we call this the polynomial identity filter. And so I'm not going to get into the details of the first step of this in this talk because they require a lot of background on semantics of quantum circuits. But the second part relies on this very cute and simple algorithm that is backed by this lemma called the short-stipple lemma for testing if two polynomials are equivalent. So what does this lemma say? Well, say I have two polynomials, and I want to see if they're equivalent. The very simplest thing you might think of is just to sample some values from a finite subset of the domain uniformly and independently. And then just instantiate your polynomials with what these values that you sample. And then once you do that, check if they evaluate to the same thing. And of course, if this check fails, then you know that your polynomials are definitely not equivalent. But what is the failure case here? It's that if they indeed were not equivalent, then the probability that this check says that they are is bounded by the max degree over the size of the domain that you sample from. And in practice, the degree of these polynomials is going to be very small, and you can make the domain that you sample from very large, like the 64-bit integers. So that's great. It gives us a high probability way of checking if two polynomials are equivalent, and circuits are polynomials, so it gives us a way of checking if two circuits are equivalent. So what does this mean in terms of our synthesis algorithm? It means that we can have, let's say, I'm on my last circuit that I've enumerated. I can turn it into a polynomial PK, and then just use the set of values that I've sampled in my polynomial identity filter, instantiate it, evaluate it, and then just insert it into this data structure according to the value that I get. So you can think of this as like a hash map where the keys are these values, and then the values are equivalence classes of circuits. And when you do this, you can just use the union bound to bound the probability that you have a wrong rewrite rule, because this is a probabilistic test. And that's going to be at most k squared. If you have k circuits, it would be k squared times the probability of one of these tests failing. And so if I have, for example, like 10,000 circuits, and they have degree 10, and I sample from 64-bit integers, the probability of having one wrong rule is going to be at most 10 to the minus 11. So it's a very small failure rate, and you could repeat this test if you're interested in boosting that. So if we revisit our algorithm and look at where the improvement is, it's basically, we don't have this nested loop anymore. You just enumerate your circuits and insert it into this data structure. And so instead of having a quadratic algorithm, you just need to do a linear pass through all these circuits. And the nice thing is that we have this handcrafted optimization as a symbolic rule, and we have a way of representing its semantics and checking if they're equivalent. And so how this work is normally evaluated is that we have a set of benchmark circuits, and we see how different tools do on reducing some metric. In this case, we're looking at 2-qubit gate reduction because remember that they had an order of magnitude higher failure rate. And so for this particular device, we can synthesize an optimizer in 1.2 minutes. There ends up being like 700 rules, and the probability of failure here is 10 to the minus 17. And the way that you read this plot is any points above the dashed line are circuits that we reduce more gates, and the ones below is like we're underperforming, and then on the line is the tools are achieve the same reduction. So in this case, we're comparing against other state-of-the-art handcrafted optimizers. This box tool is like an academic work, and then these other two are industrial toolkits. And as you can see, we're doing pretty good here. And if we revisit our landscape, there was this funny tool that was touching all of these quadrants, and it also has a similar idea of trying to synthesize rules, but it includes some manual handcrafted preprocessing. And so when we compare against that tool, firstly, we're synthesizing these rewrite rules much faster. And then secondly, when we compare them head to head, we're about the same. And I like to point out that this class of circuits that we're not doing as well, it's because they're applying some handcrafted preprocessing that's at a higher level of abstraction than the rules that we're synthesizing. And that's going to come back in future work. All right, so rewrite rules seem pretty great, but they're relatively small patterns, and they can be pretty myopic. So what can we do more? So you might remember at the beginning of the talk when I mentioned these optimizations that you can synthesize at compile time. So what is that? Well, firstly, yeah, rewrite rules are these optimizations that we're going to synthesize ahead of time. But at compile time, there's this notion of being able to resynthesize a circuit. And if you're familiar with program synthesis, this signature will look very familiar. We just have a program, and then we can extract a specification from that, namely, like I can get its unitary matrix, and then just pass that to the synthesis algorithm, and it'll return a circuit that implements that specification. And so these two techniques they have complementary strengths. Firstly, rewrite rules are fast to apply because we can synthesize this database ahead of time, and it's very easy to just search for a pattern. But on the other hand, circuit resynthesis, like we're trying to solve this search over the space of circuits at runtime, and so that's going to be quite slow. But the thing is that rewrite rules are small patterns, so they're going to be limited in the number of gates that you can have in a rule, whereas resynthesis is not limited in this way. Essentially, because it relies on getting the specification in the form of the unitary matrix, as long as if you act on a small number of qubits, it doesn't matter how deep this circuit is. So you could resynthesize a very deep subcircuit. And then finally, rewrite rules preserve exact equivalence, and it's very difficult or impossible to approximate a rewrite rule. Whereas circuit resynthesis gives you a very natural way of approximating your output circuit, and this is something that is acceptable in quantum computing. And so prior work did include both of these, but it implemented it in these very coarse fixed passes. And so the question was, can we have a search algorithm that synergistically combines the strengths of both of these types of optimizations? And I won't be able to get into the details of the algorithm, but you can assume that the answer is yes. And compared to the first one that just uses rewrite rules and simple beam search, the blue here is like the percentage of the benchmark suite that the tool does better. And then the darker color is matching, and then it's never worse. And then the story extends to all these other state-of-the-art optimizers as well, importantly, one that uses some expensive hardware. So what's next? Well, this landscape, while it looks very complicated, actually only represents a small fraction of what the quantum software stack might look like for compiling a program. And actually, we might have extra steps like converting a high-level program into a high-level circuit before we get down to this low-level assembly. And then even below that, we need to run on error-corrected hardware. And so actually, this native basis gate set, it's going to be implemented using many more gates when you try to do it fault-tolerantly. And so there are things that we might like to synthesize, such as rewrites over these higher level circuits, or synthesize some implementations for some fault-tolerant implementations for these operations. And the thing that this has in common is that we need to reason about circuit generating programs, and this is going to be a more difficult task than what we were looking at before, which is like these concrete small circuits. Great. And yeah, I just want to point out that all the work that we've done is open source in our compiler, and that's all I have. Thanks.
Great, thank you so much for that talk. So now let's open up to questions from the panel. Please go ahead.
I have never, ever before seen a talk on quantum computing where I understood the whole thing.
I'm glad.
That's an amazing achievement. Well done.
Thank you.
You did a really good job with that little square there of setting the landscape and all these different approaches. And you explained pretty well what you were doing. Because there's all this other stuff going on, so was your unique idea just applying this one theorem that let you take this very expensive equivalence test and turn it into a fairly cheap one? Was that the key insight?
Yeah, so actually the more interesting technical detail there is how you get a polynomial that represents the semantics of a circuit, but that requires a lot of extra background that I didn't have time to get into.
So I was wondering,
But
why doesn't everybody use this theorem? And the answer is there's this hard step of getting a polynomial.
yeah, exactly.
So that's the tricky thing
Right,
that you did.
right.
So was there you did something fantastic, which is you didn't try to show everything. You showed some key bits, which was great. I think that worked really well. Was there a key insight in letting you do the polynomials, or just, well, if we could do polynomials, then we could use this great idea, so let's just do it and you ground, or?
Yeah, it relies on taking this alternate view of circuit semantics. So I said that circuits are unitary matrices, but there's actually other ways of representing the semantics of what a circuit does. And so there, in particular, this Feynman's path integral formulation lets you define something called path sum semantics, and it looks like more like a function. So it's easier to see how that might be a polynomial. And yeah.
So you were sort of there's actually a big space here, and you were looking at a different part of it than other people have looked at.
Yeah, I mean, there's like previous work that introduced this idea of path sums, and but yeah.
Okay, cool. Well done.
Thank you.
I have the same feeling. Luckily, I'm not an expert on this, but today I think I roughly understand what people are working on. I think given this gigantic kind of roadmap, right? I want to know
Yeah.
I think this is always familiar with this kind of scalability kind of curves and yes. So what? How possible?
Yeah, that's a good question, and that's something I'm trying to figure out. But that's why step one is figuring out just how to do the verification task that you need to do for synthesis. And because now you're reasoning about programs that are parameterized on the number of qubits, and now so you can think of it as like now your programs have loops, and then it becomes difficult to automate it. So that's something I'm in the trenches of right now. But I remain optimistic, and I hope that we really can apply synthesis to these types of tasks. But
another thing I think I'm really curious is that when you look at synthesis on the high level program, right, and also on the low level things. So what are the key differences?
the key differences between these two?
Yeah.
Yeah, so at a high level, essentially it's just, well, the nice thing about these programs at the low level is that they use a set of gates that is not universal, so you can't do everything that you want to do in quantum computing using this. But what's good about that is that means that it's efficient to simulate it classically. So that's what's nice about working on things in this regime. And they're still useful because everything that we do for error correction uses this set of operations. Once you go high level, you do actually need to worry about all the operations that you can perform, so that's like the distinction here. But they're very similar in the structure, I guess.
Can you say a bit more about that? Because this is the future work angle, sort of what I was wondering about. What do you mean you need to be able to think about all the different high-level programs that you are working with?
Yeah, exactly. Yeah, so previously, like, we're just looking at concrete circuits that are operating on a fixed number of qubits. But you might imagine, like, if I have an algorithm, for example, I'm going to have a circuit for each, for example, if I'm trying to factor a number, I'm going to have a different circuit for, like, depending on how many bits this number has. So, like, the algorithm is parameterized on some number of qubits, and it will generate a circuit for that size. So now we're trying to reason about, like, maybe equivalence between classes of circuits that, so like a rewrite rule that holds for all sizes of qubits.
And then you're basically doing this for every kind of sub-computation of the high-level program.
Sorry, can
For every kind of sub-computation in the high-level program, you're generating these circuits for different sizes, right? I'm trying to sort of broadly understand what you're saying over there, right? Like in each of these like high-level circuit generating programs, what goes into that is kind of what I'm trying to get.
Yeah, so you need to have a way of. So actually, I'm currently focusing on the thing that is on the bottom, but like they're pretty similar. But now you need to have some, like, you have loops that construct your circuit, and you need to come up with some invariants about what these loops are doing.
I have one last question. In the interest of time, could we swap presenters as
Yes.
opposed to So my last question is, you talked about the polynomial ID filter as a way of tracking equivalence classes between different polynomials. Is there any connection to kind of classical optimization strategies like equality saturation, E-graphs? Have you looked at those at all?
Yeah. So my understanding of that line of work is that it's mostly
Hi. My research interest is motivated by one single question. How can we better reason about the correctness of real-world security-related infrastructure? Now, this problem is challenging, and to demonstrate why it's a difficult question, I want to consider an example where we implement a server that stores people's passwords. Here, we're storing people's passwords using a mutable map, and we expose two functions. You can set someone's password, and when you check someone's password, we'll just read from the mutable map and check whether the value stored in the map matches the password we provided. Now, if you ask any security expert, she will tell you, this is not secure. You don't want to do that, because if the database gets leaked, everyone's passwords also gets leaked immediately. And one way of preventing that is to do something called hashing, where instead of storing people's password, we apply a deterministic but hard to invert hash function on the password, and we store that hash into the map. And so when we check the password, instead of checking whether the password matches what we stored, we compare to see whether the hash is the same as the one stored in the map. Now, this solves the problem where, immediately it takes a while for us to crack people's password, but this is still not perfect because, in general, people do use the same password. And if we're able to crack just one person's password, there's quite a likely probability that someone else will use the same password and we crack everyone who has the same password because the same value will be stored in the map. One solution to solve this is to use something called salting in addition to the hash. Whenever we want to set someone's password, we randomly generate a number from 0 to big N, which we call a salt. And what we store in the mutable map is that we store both the salt and the concatenation of the salt and the password applied to the hash. In this case, when two people are storing the same password, there's a high probability that they will be generating different salt, and they will be hence storing different values into the mutable map. And that allows us, and so from the attacker, it's not very clear to see which people are using the same password. Now, just for this example, we can immediately see the use of randomness. And there's actually randomness in two places. We actually need to use randomness to generate the salt, but also, even though the hash function is deterministic, in order to prove security properties, it is often useful to model it as if it's a random oracle. And this brings us to the first challenge of verifying real-world security-related programs. And that is, when you have randomness, the properties we want to verify also becomes more complicated. In addition to the traditional properties we might want to verify, like checking password with the right password returns true, there are certain properties that are described in terms of probabilities. For example, checking a password with the wrong password returns false, but there is a small probability that a failure occurs where there's a hash collision. So this property only holds with a high probability. There are also certain properties that might be even hard to state. For example, that the password storage appears random to an outside observer. The second challenge with verifying real-world security properties, real-world security-related programs, is that the programs actually use quite a lot of complicated language features. Right off the bat, we can see the use of dynamically allocated mutable state for the mutable map. I can rewrite this function. If I don't want to expose the map to the user, I can try and encapsulate it and hide it within two higher order functions. And in this case, I will need to be able to support and reason about higher order functions. Maybe the language does not allow us to sample from a specific range of numbers, and the only primitive we have is that we can only generate a random 8-bit number. And for us to restrict the domain of the number generated, we need to implement it using a rejection sampler. In this case, we need to be able to reason about unbounded looping. Maybe the clients of this server is scattered all across the world and they might send requests at the same time, so we might need to be able to reason about concurrency on the client side, where requests are sent to the server at the same time. But there's also might be concurrency in the implementation. For example, in Linux systems, the way we generate numbers is that we read from a certain file, and there's a concurrent kernel thread that repeatedly writes random entropy bits into this shared file for different applications. So stepping back, in order to verify real-world security programs, we need to overcome these two challenges, where we have to reason about probabilistic properties and also reason about programs that use a wide range of language features. Let us see how we can attack these two issues independently first. When I think about the first issue about reasoning about probabilistic properties, there's quite a lot of different prior work on verifying these probabilistic programs. There's the weakest pre-expectation calculi for reasoning about error bounds and expectations, a lot of different coupling-based logics for reasoning about relational properties. There are certain logics like Lilac and Bluebell which realize separation conjunction as probabilistic independence, and many, many more. However, these techniques often suffer the second problem, where the language they consider have certain trade-offs. For example, we might not be able to reason about shared state or concurrency with these techniques. To tackle the second problem, we can actually use IRIS, which is a higher order concurrent separation logic framework that is formalized in the proof-assistant ROC. And in recent years, there's actually quite a lot of work and success in using IRIS to verify programs with these challenging features that I've just shown you, like higher order functions or local state. The problem is that there isn't that much work in actually using IRIS to prove probabilistic properties. And hence, in my PhD, I try to combine the best of both worlds, where I develop probabilistic extensions of IRIS to reason about highly expressive probabilistic languages. And in this talk, I want to showcase a couple of logics that my collaborators and I are able to develop and reason about these complex programs. My PhD is roughly split into two stages. In the first stage, I develop IRIS logics specifically for reasoning about sequential probabilistic programs. And currently, in my second stage, I am extending the logics I developed before to reason about concurrency as well. To motivate these logics, I want to present a slightly simple example where we use the hash function again. Here, we are given two different inputs, and we hash these two inputs, n and m, with some deterministic hash function where we produce x and y. And in security, as I mentioned before, as I hinted before, it is often useful to model the hash function as a collision-free random oracle. And by collision-free, I mean that different inputs are mapped to different outputs. And so we might want to prove a specification as so, where if m and n are different initially, the two values produced, x and y, will also be different. However, this is not always the case, because there is a small probability that a collision might occur. And we might want to reason about this precise error bound where an error might occur. To do so, my colleagues and I developed ARIS, which is a higher order separation logic for reasoning about error bounds of higher order probabilistic programs. The key idea of ARIS is that we internalize probabilistic error as a separation logic resource, which we call error credit. Error credit is written with this assertion, which we can read it as up to epsilon, and this epsilon is a real number that ranges from 0 to 1. Intuitively, if you own epsilon error credit, you are trying to prove the goal with at most epsilon probability of an error occurring. And you can see this more intuitively from the adequacy theorem, where if you can prove the Hoare triple on the left, assuming epsilon error credit to start with, then in reality, when you run the program, the probability that you get a value not in the post condition, hence an error and hence an error result, is upper bounded by epsilon. And in the logic of errors, there are various rules, various flexible rules that allows you to spend error credits to avoid undesirable error results. For example, if with this rand n operation that samples uniformly from 0 and n inclusively, I can provide a list of numbers which I consider to be bad, and I provide an error credit proportional to the length of this bad list. And I can ensure that I will not be able, that the result of this rand n primitive will not be in the list. To show that this approach of error credit is very flexible, we proved a lot of examples, including this one where we actually provided a specification for the collision-free hash function I just provided, where you have to provide an error credit that is proportional to the number of times you have used the hash. With this specification, we derived an even more interesting specification where now the error credit is not proportional to the size of the hash, but constant. This can be done where we amortize the error credits across a fixed number of insertions. And this is easier to use from a client perspective because I don't have to know how many times I have used the hash function before when supplying the right amount of error credit. And it's also important to state that we're able to derive this specification just from the specification of the non-amortized version. And with this specification, to show that this is expressive and useful, we use it to implement various data structures like a Merkle tree and an unreliable data storage system. And we can show very nice error bounds of the probability of getting a right results when using these data structures. Error bounds are not the only property we want to reason about probabilistic programs. Sometimes these properties are described relationally. Take these two programs as an example. On the left, you have a pseudo-random function where each time you call it, it generates a random number. On the right is a pseudo-random permutation where we create a reference that points to an empty list, and every time we call it, we generate a number that is not in the list and append that, concatenate and add that into the reference. So in other words, the program on the right will always generate unique random numbers. And for the first few times you use these two functions, they appear to be somewhat similar. Well, not completely identical, but approximately similar up to some error, epsilon. And my colleagues and I developed a proxys which reintroduces the idea of error credits from errors, from the unary setting to the relational setting, that allows us to reason about this particular approximate refinement where we can compare two approximately similar programs. And this approach, we're able to reason about quite a lot of interesting security-related examples, such as the PRP-PRF switching lemma and the security of an encryption scheme. We also implemented a binary logical refinement relation within the logic of a proxys that allows us to prove contextual refinement, and we use it to prove the correctness of a B+tree sampling scheme that uses a complicated rejection sampling argument. Now, errors in a proxys are logics for sequential probabilistic programs, and currently I am extending these to reason about concurrency as well. And currently, colleagues and I are able to develop logics of Canaris and Foxtrot, which are the concurrent counterparts of errors in a proxys respectively. One must emphasize that this extension is highly non-trivial. Reasoning about concurrency is difficult, reasoning about probability is also difficult, and reasoning about the combination of them is just pretty challenging. And here I want to highlight some issues that we encountered when developing these logics. For example, in Canaris, in order to support specifying modular specifications of concurrent randomized modules, we realized that we have to capture something called randomized logical atomicity, and we will need new key ideas and features in order to capture this notion. In the relational case, it's even more complicated because certain rules that are sound in the sequential case suddenly are suddenly unsound and are not directly translatable to the concurrent case. In particular, in Aproxis, we use something called pre-sampling tapes to reason about complex distributions. And the rules that we write for pre-sampling tapes, some of them are actually unsound in Foxtrot, in particular the ones where you have to pre-sample on the right-hand side. And so to tackle these issues, we have to completely redesign the model of these logics and introduce new ideas that introduces new logical facilities and proof techniques such that we can recover as much expressiveness of the logic as possible. Some of the examples we're able to verify in Canarix and Foxtrot includes a thread-safe hashes, which is similar to the hash specification I presented before, but now it is thread-safe in the sense that if two different or multiple threads use the same hash, the keys, the hashes will be consistent. So if two threads hash the same key, they will all produce the same output. We show that this specification is expressive by using it to implement a concurrent Bloom filter data structure. And we are able to show strict error bounds of getting a false positive with this data structure, which to the best of our knowledge is the first because of its interaction of concurrency, probability, and local state. In the relational case in Foxtrot, we're able to verify the correctness of a sampling function in the cryptographic library Sodium. In particular, we're able to show that its implementation is contextually equivalent to an idealized one. And it is important to emphasize that even though the implementation doesn't use concurrency, we're quantifying over all possible contexts that might even use concurrency. And so this gives us high degree of confidence that the sampling function is thread-safe and can be safely used concurrently. Now that I've introduced you a couple of logics, let us take a step back and consider our original problem and ask, can we prove the properties of this password storage system? And the answer is that if we just want to prove the first property, where checking the password with the wrong password returns false with a high probability, we can express that as an error-bound result, and we can use errors to verify it. For the property where we want to reason about the password storage appearing random to an outside attacker or observer, this can be stated as a relational property, and we can use Aproxis to prove it. In the case where we even have concurrency on the client side, we can now use Canarix or Foxtrot to prove the same properties. However, if we have concurrency in the implementation for this particular case, it turns out that it's not possible to verify certain security results using the logics I just presented. And the reason for this is that the concurrency model of Canarix and Foxtrot are a bit too powerful in the sense that the schedulers we use to decide which thread to step has too much information about the whole program configuration. So an adversary can see the numbers generated into the file and decide which application would use certain bits. Now, this is not very realistic because in the real world, adversaries might not have complete information of everything you have in your software. For example, an adversary might not be able to see your secret keys. And hence, if we want to prove some interesting security results, we need to be able to reason about more schedulers with restricted power. And one future work in progress is that I want to develop logics and inspired by Canarix or Foxtrot, where we internalize the idea of restricted schedulers and prove more interesting error bounds when we're quantifying over more realistic schedulers. In conclusion, verifying real-world security programs are challenging, and that is because we often have to reason or prove very complicated probabilistic properties. And these programs actually use quite a lot of complicated language features. And in this talk, I showed you a couple of logics where I'm able to take one step closer to achieving this dream where we can verify interesting properties of these programs. And in the future, I want to continue refining and improving the concurrency model of Canaris and Foxtrot that better reflects real-world adversaries and apply these logics to verify actual implementations of cryptographic libraries and protocols. Thank you.
Great, thank you so much. So now, we go to questions from the panel.
I'll start with what's up on your conclusion slide. In fact, the very last line. In order to verify actual implementations of libraries and protocols, you would need a logic that applies to the languages that they are implemented in.
Sorry, couldn't.
You would need the logic to actually be be able to verify code written in the language that the code is written in, right? So how do you see that going? Do you need to design Iris from, C or something?
So I think that's a very good point. That is, like, if we want to be as realistic as possible, like, even though the language we consider do have a lot of features, there's still like certain trade-offs, right? As let's say in C, there's a lot of like behavior that's very hard to model. We don't have like, certain, like, we're not able to reason, for example, about floats or double because we don't have real numbers. And I guess this is somewhat like a trade-off. And the way I see it is that, we just try our best to reflect like actual implementations as possible. I think it gets quite hard if you try to get everything, and this is another research topic by itself, but we do try our best to reflect real-world implementations, mostly, and I think most implementations, hopefully they don't use too much complex behavior of certain languages.
Yeah, I mean, there is this gap between verifying what looks like a very realistic implementation that's written in nonetheless, not the actual language that it's implemented in. So you end up not verifying the actual implementation. And I've always sort of been intrigued by how do we create a systematic way to bridge that gap. But that is a little far.
Yes.
I admit. Let's see. Maybe I'll let the others go first. And then
I think just to follow up on this implementation point, I really like the examples you set up. It's really helpful in terms to understand all the concepts precisely on the example. But I'm curious about this real the experiments you have done through this number of works, and what are the design or any implementation you have verified, and how much effort you put into the verification, and any sort of automation in the verification process?
Yes, automation is pretty difficult at the moment because a lot of these probabilistic properties are not easily done with automation. Most of these examples, because we prove it using the proof assistant Rock and Iris, so we have to do it by hand. But I do, I do feel like some of these programs are pretty significant and do push the states of the art because of the reason that we can prove a lot of the things modularly. So as an example, like a case study as so, we're able to prove these things in different layers. So for example, when I'm verifying the unreliable data storage system, I only use the specification of the Merkle tree. And when I'm verifying the Merkle tree, I only use the specification of the amortized one. So it gets a bit easier, the fact that we have that nice modularity and we can split things into different layers and allow us to prove the programs.
I want to understand, can you just pinpoint what are the key contributions? I know this is a very, very difficult question, and people have been longing for solving verification of probability, concurrency, and whether the real time is also on your roadmap. And these are all the things I think we are trying to address. And when you put all these challenging things, what are the kind of the key insight, the key
So the whole, so I think there's quite a lot of interesting ideas. Like for each of these logics, they contribute something technically interesting. For example, in Canaris, we actually have to capture this idea of randomized logical atomicity, which is the idea that the module can commit to some random choice in just one single, or we can reason about it as one atomic step. I think the way I see it is not like a single like key idea, but the result of it, in the sense that we're able to reason about concurrent probabilistic programs that have a wide range of these language features, which is very difficult to do so in other previous techniques.
I just want to commend you on that. This is a truly visible combination of features to have and be able to support it.
Thank you.
So, yeah, building on what Amal said there, these things always sort of make my brain explode. Like you got this complication, and this complication. Do I need a brain as big as yours or Lars to get benefit from your work? Or is there something in there that's fairly a simple but useful insight that somebody stupid like me can make use of?
I think the answer is yes, because like say my experience with like developing these, like, you know, I have to think a lot about how to build the model, but for a user, you don't have to know how the model is implemented in order to use the very intuitive program logic rules. So from your perspective, you're only interacting with the program logic rules that we have implemented and we have proven to be safe. And these rules are much more intuitive, and it's pretty easy to use. And you don't have to unfold the definitions all the way to the model in order to use it, because we have already given these like API, for a very simple API for you to use and prove it, to prove certain program.
I was hoping that so there's this list of rules, I can just use them. But was there like a bathtub moment where you rose up and said, Eureka, and you suddenly had some interesting insight?
Like for me, for myself, like how I came up with these?
Yeah.
I think it's a lot of time in the shower. Most of these ideas, like a lot of these techniques are motivated by examples. Because for example, I want to say reason about rejection sampler. So like a lot of these techniques are just very motivated by examples that we're not able to reason about. And for each of these like techniques or these logical facilities, they just target that particular problem. And for me, it's a lot of experience of seeing what kind of rules work previously, just even without the probabilistic case, and see whether we can like try and fit things together with the probabilistic world. And you know, some ideas are easier than others, but I think, you know, just having like seeing a lot more experimenting with the proof assistant really helps, because there's a platform for me to test out and try different things to see whether we get nice properties.
Motivation for their practical application in things like machine learning and so on. Do you have a story for the practical applications of probabilistic programs with shared memory and concurrency? Or is this more about a theoretical view on how things can work?
Sorry, say again?
Do you have a view on practical applications of probabilistic programs needing shared memory and concurrency features? Do you have a story for what kind of programs might exist in the real world that use those combination of features?
Well, that uses both. I think a lot of the data structures that I have presented, like, you know, like say just the Bloom filter, it uses shared state, and you know, you will have to use, you know, probability to reason about the hash. So I think that is a pretty good example where you need the both the local state and the concurrency and the probability.
Do you need shared mutable state for that example?
Yes, because the hash, you know, in order to model that hash, you know, it has to remember the values of the keys you have hashed before. So if you hash like say 0,
and you update it with fine-grained concurrency, is that the point?
well, I don't see other way of doing so. Maybe we can like discuss this later.
No, that makes sense. That's all the detail I want to go into. Then I guess my last comment in terms of presentation style, there were one or two slides where the code names you had given to the
Thank you very much.
Thank you. Yeah, I'm Ben Mikek from Georgia Tech. And to start with, we maybe need to revisit a question of what is static analysis. So I've put here an example workflow that we might use to do some kind of analysis. We start with an input program. We compile it to get some output like x86 assembly. Then we apply some static analysis tool to it and get out a result. I've put in this example SMT solving. And we can interpret that result to draw some conclusions about the input program. There are lots of variations of this. We might directly analyze the input source code instead of running through a compiler. We might do this on a we might do this on a compiler IR instead of on assembly. And there are lots of static analyses built into the existing compiler also. But this is just one example workflow that I'll discuss in today's talk. Static analysis is good, and I hope I'm to some extent preaching to the choir here, because it can provide formal guarantees, and we can therefore use it for safety critical systems. For example, I think many of us traveled here on airplanes whose software might have been verified using static analysis, and then gotten off at the airport and gotten on a train whose software was also verified using static analysis. So this sounds like a great story, but there's a big downside here, which is that static analysis is very difficult to do. There are lots of existing bottlenecks in static analysis tools. And today I'm going to talk about how we might go about alleviating those. And those bottlenecks can take two different forms. There may be a lot of manual developer effort involved in developing a particular static analysis tool. And second, even once we have a tool, that tool might have a long runtime, it might not be scalable, it might not be able to handle large inputs. And so those bottlenecks, some examples include SMT solving, where there are thousands of constraints that existing SMT solvers can't solve and we can't scale up. Translation validation, where there are larger programs whose equivalence we can't prove. And of course, compiler verification, where there are existing efforts like CompCert, where we can verify a chunk of an existing compiler for a subset of a language, but we can't verify all of the optimizations that we'd like to be able to do in modern programming languages with compilers. And so in today's talk, I want to think about what is the cause of these bottlenecks. And one possible reason that we have these bottlenecks is that we tend to think of there being a wall here in between the compiler and the static analysis that we do. So there's static analysis built into the compiler, but if we're using some external tool, we can't take advantage of any of the knowledge that's embedded in the compiler. And so there's external information not directly contained in the program that we give as input to the static analysis that could help improve the performance. And the kernel of my idea is that we can extract that information from the compiler and feed it into the static analysis application. So in some sense, I'm going to propose that we can tunnel underneath this wall. We can gather information from the compiler, then filter it for a particular static analysis application, and then pass that information into a static analysis tool to improve its performance, scalability, what have you. So my vision in this talk is that we want to extract and harness the information that's embedded in a compiler to improve existing static analyses and make them more scalable. And I'm going to discuss how we do that in three parts. First, I'll talk about SMT solving, which is one example where this is possible. Second, I'll give a second example of translation validation. And then third, I'll discuss how we might generalize this framework and my vision for the future. So to begin with, SMT solve. SMT stands for satisfiability modulo theories. It's an extension of the SAT problem where we can have not just Booleans, but also bit vectors, floating point numbers, real numbers, etc. And this is a major bottleneck in static analyses like, say, symbolic execution, where SMT solvers can't solve many constraints that we want to be able to solve to be able to analyze large programs. The existing approaches to improving SMT solving are usually either develop a new solver or extend an existing solver. Both of these approaches require lots of manual effort, and they require a lot of domain knowledge of the existing solver and of the problem, of the subset of constraints that you're interested in solving. So instead, I propose that we can harness the existing compiler knowledge to simplify constraints before we solve them, and thereby speed up the solving process. We start out with, with an initial SMT constraint that we can solve with a solver, but it takes a long time, or maybe it even times out. Let's say we can get the result that's either satisfiable or unsatisfiable. What we want to have is a simpler SMT constraint that we can also solve with a solver and get a satisfiable or unsatisfiable result. And importantly here, we want to get the same result both times, so we need the simple constraint to be equivalent to the complicated one. And in my work, I found that we can use the existing compiler optimizations to simplify constraints, to go from a complex one to a simple one, while preserving satisfiability. And this is work that was published in FSC 2023. It's called SLOT, SMT LLVM Optimizing Translation. It works by starting from the original constraint and translating it into compiler IR. Then we can apply the existing LLVM optimization passes, but we do some filtering here to only passes that are likely to help in SMT solving. So for example, we filter out passes like vectorization that would just make constraints more complicated. We then take the simplified IR program, convert back to an SMT constraint, and in the end we have a constraint that hopefully will be much faster to solve and still has the same satisfiability or unsatisfiability as the original input. So to understand how this works, here's an example SMT constraint. This is derived from an underlying C program, and the question we're trying to answer here has to do with whether an integer overflows. This constraint Z3 takes 600 seconds to solve this constraint nearly. And so I think you'd agree with me that the constraint on the right, which we can achieve with SLOT, can be solved much more quickly than that. And indeed, Z3 can solve it in just 2/100ths of a second. Now, this looks great for one constraint, but we need to evaluate it on more than one constraint to see if this works on average over many constraints. We've also extended it to not only apply to bit vectors and floating point numbers, but also in work published in PLDI 2024 to real numbers and integers, which are unbounded, so not bit vectors. We evaluate this on the standard SMT-lib benchmark set, and we find that SLOT can solve thousands of constraints across the 4 theories on which existing solvers time out. And we achieve large mean speedups for all of the subject theories, which you can see here. For bit vectors, 1.27 times, and larger speedups for floating point and the combination of bit vectors and floating point numbers. Here's a graphical representation of our results for floating point numbers and bit vectors. And as you can see, these are grouped by original solving time. And as you can see, for all of the groupings, SLOT is able to achieve some speedups. And the speedup doesn't depend on the solver or the initial solving time. So overall, we can get the compiler information that we're interested in here, which in the case of SMT solving is the logic of the optimization passes. We extract it, but in a sense it's backwards because in fact we're converting the constraints into compiler IR in order to apply the optimizer. We perform filtering in that we filter only to the optimization passes that are likely to be helpful for speeding up SMT solving. In the end, we're able to dramatically speed up the solving of SMT constraints. But even more information is available inside the compiler. So we'd like to get access to that, and that might be useful for even more static analysis applications. And that brings me to part 2, where I'll discuss how we can do that in the case of translation validation. So translation validation, the problem that we face is we have an input program, we give it to a compiler, and we get the result of the resulting output program. And we want to verify that the input and output programs have the same semantics. This is an alternative, kind of a second best answer to doing full formal verification of the compiler, because that's impossible to do for some of the optimization passes in modern optimizing compilers. There are many existing tools to do this. One of the famous ones is Alive2 for LLVM. But these tools can struggle with programs that have complex control flow like loops. And in particular, most of the existing approaches to translation validation are bounded. So they can unroll loops to a fixed bound and verify that they're equivalent. But if the number of loop iterations depends on input, then these existing approaches struggle to handle that. The traditional workaround to this that goes all the way back to some of the seminal work on translation validation by George Nekula in 2000 is something called program alignment. Here, we take an input program that contains a loop, and we want to line up iterations of the loop in the input program with iterations of any loops in the output program. And this is useful for handling optimizations like loop vectorization that traditional translation validation approaches struggle with. So to give an idea of how this works, here's a simple program that just contains one loop. After we pass this program into LVM, the Clang compiler, we get the program on the right, P1. This is a much more complicated program. What's happened here is that we've inserted this new vector loop, and this loop performs 8 iterations of the input loop at once in vectorized instructions. And then we've also inserted this loop labeled scalar, which I like to think of as a cleanup loop, so that, for example, if we ran the original loop 9 times, now we can, the vectorized loop will handle 8 of those iterations, and any of the leftovers will be handled by this loop marked scalar. So this is a vectorization transformation that would be difficult to verify with traditional translation validation approaches. To align these two programs, I'm going to talk about how we can associate their states and their transitions. And in doing that, I'll refer to these program points, which are marked with circles, and transitions, which are marked with T with a subscript. So starting with P0, we're just going to construct the control flow graph. Note that this is maybe a little bit backwards from control flow graphs you would see in a traditional compilers class, because we have program points as the vertices and basic blocks as the transitions. But we have the program, the entry point of the program. We can enter this loop marked 2 with a loop transition, and then we can go to the exit of the program at point 3. Similarly, for P1, we can do the same thing. We start at point A. We can transition into the vector loop, which also contains a loop. We can also then transition into the scalar loop, either from the start immediately or from the vector loop. And finally, we reach the end of the program. And to align these two programs, we need to pair up their states and their transitions. So in this talk, I'm just going to ask you to believe me that the state pairing is correct, and we're going to focus on the pairing of transitions. So first, we pair up the states 1 and A. We pair up the state 2 and B. And for each of the transitions, we just mark them by concatenating the transitions in P0 and P1. We do the same thing with the pairing of 2 and C, and finally with the pairing 3 and D. There's a lot of moving parts in the background here, but I'm going to ask you in this talk to zoom in on this important fact, that the transition on the 2B state pair has an 8-to-1 mapping. So 8 repetitions of the loop in P0 corresponds to 1 repetition of the loop in P1. And that's the important information that we need to get at. If we know that association, then we can use a solver or some other strategy to check whether, in fact, 8 iterations of T2 corresponds to 1 iteration of TB. But it turns out that getting that information in general is quite difficult. The existing approaches to getting this, and I'll focus on a work from Alex Eichen's group from PLDI 2019 that does this, is to actually run both programs, collect a concrete trace of what each one is doing, and then infer an association based on those concrete observed values. So if we give both programs the input 8, in P0 we would run the loop 8 times, in P1 we'd only run the loop once. For 16 we'd have 16 and 2. For 20 we would run the initial loop 20 times, and in P1 we'd run the vectorized loop only 2 times, with the additional 4 handled by the cleanup loop. And we can keep doing this for many inputs. With enough data, we can then search over a space of linear transformations from one to the other. And if we squint pretty hard here, we might be able to conclude that this association that's shown at the bottom, that T2 represents 8 iterations, 1 iteration of T2 corresponds to 8 iterations of TB, and 1 iteration of, the number of iterations of TC. And from that, we can derive this 8-to-1 mapping that I talked about. But I think that already in this example, you can see that there are some problems here. Even just with 4 inputs, this relationship it isn't obvious that this relationship is correct. And in fact, the inputs for a more complicated program might not even cover all of the possible control flow paths. Moreover, if using inputs like this doesn't take any advantage of the compositional nature of compilers. So there's a lot of information that's lost by treating the compiler as a black box. And so our strategy is that we can extract that 8-to-1 mapping, the information needed to align the programs, directly from the compiler without needing to run either program on concrete inputs. So we do this by instrumenting each optimization pass to produce transformation records. These are records of what transformations the pass has performed, and in particular, these transformation records contain this 8-to-1 mapping that I've been focused on that allows us to line up the programs and check whether they're equivalent or not. Collecting transformation records means that we can update the program alignment compositionally. So every time an optimization pass happens, we can update our program alignment to reflect the optimizations that were performed. And there's a little bit of a wrinkle here, which is we don't want to trust the compiler to be doing the right thing, because the whole purpose of this is validating that it does. But we will trust the compiler to accurately tell us what it did, just not that what it did was the right thing to do. So this work is still in progress, but we've done a preliminary evaluation on it. We've instrumented the LLVM's loop vectorized pass to record the basic block associations and that 8-to-1 mapping that I showed you. And the transformations for the other passes are primarily derived from the existing LLVM debug information. We've evaluated this on a benchmark set of 38 programs from the test set for vectorizing compilers. That's the same benchmark set that was used in the related work from 2019 that I mentioned. And our approach is able to successfully align 27 of the 30 programs that are vectorized from this set. So overall, the information from the compiler that we're interested in are the transformation records, in particular, in this example, the record of how the program was vectorized. Our method of extracting it is to instrument the compiler passes to give us feedback about what transformations took place. And our method of filtering is that we're only interested in transformations that moved around or inserted or removed basic blocks. We don't care about transformations that only modify single instructions like people optimization. And the results are that we can line up a large number of programs from the benchmark set. We don't need to run them with concrete inputs, and we can thereby validate that they're equivalent for programs where existing approaches would struggle. The only downside is that this approach is still fairly narrowly tailored to optimizations that affect control flow. And so in part 3, I'm going to talk about my vision for how we might extend this to be a more general framework. So in part 1, I talked about SMT solving, and we discussed all of the 4 elements here, what compiler information we want to get out, how we extract it, how we filter it, and then what results we can achieve. I also discussed that for translation validation. But my vision for the future is that a user should be able to bring their own analysis and then use some framework that we develop to extract the compiler information needed for that analysis to speed it up or enable it to handle more cases. And the way we might do this is that for what particular information we want, that's something that's likely to come from the user. The extraction method will be a general instrumentation framework where we instrument low-level APIs of the compiler or other transformations that it performs to extract the information it contains. And the filtering will depend on the user-specific use case, and the exact filtering of the instrumentation results can be inferred from the particular analysis that the user provided. And in doing so, we should be able to speed up the static analysis and be able to handle larger cases, improving the overall performance. I haven't talked about filtering much yet in this talk, so I'll briefly mention that. What you see on the right is the result of this generalized instrumentation of all of the insertions and removals of instructions and basic blocks for LLVM. This goes on for 400 more lines beyond what's on the screen, and that's only one pass. So there's a lot of information contained in here. That means that filtering is going to be required. On the right, I've shown an idealized version of what this trace looks like. So here we have insertion and removal of basic blocks and instructions. And in the case of translation validation, in the running example, we would want to filter to only look at operations that insert or remove basic blocks. We don't care about what's happening to individual instructions. So in this case, we would be instrumenting functions, basic blocks, and instructions, but we would be filtering to only only transformations that remove or insert basic blocks to do translation validation. And there's some trade-off here between if we collect more information, if we cast a wider net, then we have to do more filtering, and vice versa. If we instrument less, then we have to do less filtering. So my vision is, after the 2 examples that I gave, to move closer to allowing the user to bring their own analysis and extracting the information that they need for that analysis. We want to reduce the manual adaptation effort that's been required for the existing use cases that I've shown you. And there may also be more applications. So abstract interpretation comes to mind, compiler verification comes to mind, and there are other use cases where extracting the information from the compiler could benefit static analyses and simplify the problem that they face. Overall, if you're familiar with eBPF, you can think of it as an analogy that what I propose to do is to instrument LLVM to extract the low-level operations it performs and achieve something like eBPF, but for the compiler, where the use case is a static analysis. So in conclusion, external analysis from the program can help alleviate the bottlenecks in static analyses, and I propose to get that information out of the existing compiler. We extract the compiler information, we filter it, and we pass it back into an existing analysis tool. And I discussed 2 working examples where we've done that so far, and then my vision for the future work to extend this to allow users to bring their own analysis. I'll quickly thank my collaborators, Chirun Zhang, my advisor at Georgia Tech, also Jinghao Jiang, who's a master's student in our research group, and Tom Reps from UW-Madison, all of whom have helped me develop this research substantially. And with that, thank you very much, and I'd be happy to take any questions.
That's great, thanks so much. I'm going to buck the trend and ask the first question myself for this one. So with the very first project you did, where you were taking the SMT queries and effectively optimizing them through a compiler, the fact that you managed to optimize your first example all the way to false, does that suggest that actually Z3 itself should be trying to be more aggressive in optimization and has missed obvious things it could have been optimizing, or do you think it's more appropriate that the compiler is catching these things and Z3 couldn't?
So I think in many cases, I think that Z3 probably could be extended, and so could the other existing solvers. So in that example, the compiler was able to translate it all the way to false. That's not true in the general case. It can simplify without doing that. But actually, in the slot paper, I didn't talk about it in this talk, we evaluated which optimization passes contributed the most, and it's mostly like people optimization. So that suggests there are really pretty simple rewrite rules that are present in the compiler, but not in the SMT solvers. And that actually varies from solver to solver. So different passes have different effectiveness for the different solvers. So I think actually translating to LLVM has the benefit that we can just treat it like a black box, and if somebody comes around and develops a new compiler optimization, we immediately get the benefit from that. But in the long term, it would probably be helpful to try to move some of those things inside a solver so that they could be more trusted.
I was just confused on one thing. So you gave 2 examples, sort of being this general pattern. I can see how the second one fit this pattern. The first one doesn't really seem to. It's just you do the first steps there, and then when you're doing the second step, you reuse the compiler again. It's not like you're taking information from the original compilation pass. So I don't see how the first one fits this particular pattern. What am I missing? Or are you just trying to slip one by?
No, definitely not trying to do that. So the general pattern here is that we can extract information from the compiler to improve the static analysis applications. And I guess maybe you're getting at the fact that maybe the original program was compiled before we generated the constraints.
You're getting information from the compiler, but
Right.
not from the original compilation pass. So your first example doesn't seem to me to match this picture.
Oh, I see, okay. So I think here, we have to think of this, so I've put example C, x86, and SMT solving as the examples. But we could think of this very differently. If we think of the input program as an SMT constraint, then this pattern, I think, matches pretty exactly the first use case for slot, right? So I guess I've put C and x86 here as the particular examples, but we could have other languages there, and we could think of SMT constraints themselves, even if they aren't derived from a classical program, as the input programs.
So what would correspond to the compiler information you're getting from the compiler then?
The existing optimization passes in LLVM. So we're essentially taking, I agree with you, it's a little bit backwards compared to the second use case, because essentially our method of extracting the information is inverted, right? We're actually converting our input into compiler IR to simplify it. But I would argue that that's really just a practical workaround for taking advantage of the compiler optimization logic. It's just, it's kind of the engineering method of getting at the information embedded in the compiler to speed up SMT solving.
Right, we can agree to disagree. I don't think it's a big point. For the second one, right, the key idea is just, oh, the compiler knows that it's 8 instances of this loop, 1 of that.
Mhm.
That seems a really great, obvious idea.
Hmm.
Why did nobody hit on that before?
So I think that in general, people who do static analysis are skeptical and don't want to trust the compiler. I kind of represented that with this wall here. And there's some truth to that if we're trying to verify what the compiler is doing, we shouldn't trust it. So I think the real insight in that use case is that we can trust the compiler a little bit, but not fully. We can trust the compiler to tell us accurately what it did, but not that what it did was right. So I think that's the real insight that allowed us to notice this opening.
Great insight. Do you have other, for your future work, other applications of that insight that you'd like to try?
Yeah, so it's just briefly mentioned on the slide, but the application of abstract interpretation, where we might be able to extract information about ranges from the compiler. That's one case in which also, I think this trade-off, the specific will be a little bit different, but in general, the topic will be the same, because we may be able to trust the compiler to accurately reflect what it did in response to the range computations, but not necessarily that what it did was the right thing to do at the same time. There's a second example I showed in the filtering slide where we wanted to insert and remove, we captured the insertions and removals of instructions in basic blocks. And if we wanted to do translation validation for a different type of domain than this vectorization I showed. So for example, one project I've been thinking about is some of these augmentations to LLVM that do bounds checking. We may be able to instrument the compiler to tell us where instructions are inserted and removed, and by just analyzing that trace, notice cases where translation has gone wrong, so basically miscompilations. And so that's another case where we don't trust that the compiler has done the right thing, we trust that we can accurately reflect what it has done, and then we analyze that information to determine whether the programs are correct.
So I'd just like to jump in here.
Yeah.
I would say, in a way, people have thought about something
Hmm.
like this before, about extracting information from the compiler,
Mhm.
or getting the compiler to preserve it. I think type-preserving compilation is the way of doing it,
Hmm.
right? Because if you ask the compiler to take a source level type and slowly transform it down to a low-level type, what are you doing? You're saying, can you produce some evidence for me for what shape of code you are producing,
Mhm.
right? And then you can carry type-preserving compilation further into evidence-preserving compilation, which is kind of what your part 2 in order to guide translation validation
Hmm.
makes me think of, because you are saying, dear compiler, can you produce some evidence of like how you are transforming
Hmm.
the code? Just like, in type-preserving compilation, the translate types at the very target level are describing the shape of the code that the compiler is generating.
Mhm.
What is that doing? That's saying, this is my invariant. This is
Hmm.
my evidence that I, produced code of this shape.
Mhm.
So these ideas have been around. When you started, I was sort of like, this is like type-preserving compilation. But of course, you're doing something much more advanced than
Hmm.
that. And what's fascinating to me in this, I've always thought of type-preserving compilation as, oh, I have to write a whole new compiler. But maybe the challenge for you in your future,
Hmm.
part 3, is how can you you had compiler verification up there as an application
Mhm.
part 3. So how can you take existing compilers and kind of build some sort of harnessing,
Hmm.
framework into the compiler so that I can easily go into an existing compiler and turn it into one that is either a type-preserving compiler or pre-preserved compiler, preserve some particular kind of static analysis, whatever information I'm interested in. Is there a way to kind of take existing technology and suddenly start to get all of this? Because I always think, whenever I talk about type-preserving compilers, people are like, yeah, but you're going to have to build a whole new one, right? And that's the point. That's maybe a long-term investment.
Yeah, yeah.
So that's maybe what I would think that if you think about it in those very rough terms, it's really exciting to me.
Thank you. Yeah, I think I'll briefly say something about that. So I think probably the first step in that direction, which I think we've mostly taken, is by instrumenting the compiler, we can probably get out enough information to then look at the log and analyze, was it type preserving? Did it have some other property? So that part's pretty easy. Then the next step after that of going from that to modifying the compiler so that it always is type preserving, that step is a bit further in the future, I think.
That's like validating.
Yeah.
We have a question in the room, actually.
Yeah.
Yeah, the question is short. I'm not sure what you mean by instrumentation. Clearly, you don't mean the optimization remarks of LVM. You also don't seem to mean the instrument function like create basic block, because then you wouldn't need to trust the compiler. We know it creates a basic block. So what is instrumentation?
So I think actually the second part is roughly correct. So instrumentation, in the sense I've used it here, is, in the way we've realized it, is instrumenting the low-level operations like creating a basic block, creating an instruction, deleting an instruction. In practice, because there are lots of engineering details in this, we've combined that with the existing, both the debug information and like the existing debug statements in LVM. So what I call the transformation record is like an abstraction for containing all three of those pieces.
I think I really like the idea, which is very cute and effective.
Thank you.
But since the compiler is just a transformation of the source code to a binary, right? And all the whatever optimization you're using and the result you got supposed to be a known knowledge for the program analysis. So if you know what are the things you really need, you could actually get information without going through the compiler, right? In principle.
Like rerunning the analyses that the compiler did, yeah. So I think it's maybe a little bit more nuanced than that. So if you wanted to get access, I gave the example of like range analysis, then that's definitely true. You could just run your own range analysis again. But the transformations that the compiler performs are a little bit different from that. Because in this picture, if you only look at the program after it's been compiled, you only see it post-transformation. And in general, you might not have seen the pre-optimization version of that. So I don't think that there's a way from just the text of the optimized program to go back and see what was done previously. And it's those actual transformations, in addition to just the analysis results, that can be useful in actually both of the applications I showed.
Yeah, I'm just thinking because we're working on something to do the reverse. I think this could be very much helpful from the binary to source code.
Yeah, like lifting, you mean?
Yeah.
I think.
I want to really understand the complexity or the challenge part. Why when the optimization kick in, and then you miss the mapping, the direct mapping. This is the part I think if you really think about lifting, you need to really work hard.
Yeah. So I guess in some sense, if you have a complete record of every low-level thing the compiler did, then you can replay it in reverse, right, to do lifting. The problem is that in most cases we're interested with lifting to do, we want to do lifting of programs where we don't have that kind of information. So I think there might be a bit of a middle ground where we could say, this is something I've been thinking about in the security world. If, let's say we have a binary and we want to determine which source program it came from a set number of candidates, like a malware toolkit, for example. Well, we might be able to compile all of the candidates, look at the traces, and then try each one or something like that. I think that might be a first step down that path to using this type of approach for lifting.
Great, thanks so much.
Thank you.
Okay, everyone, we've gone a couple of minutes over time, but it's a break now. Thank you all for your patience. We will be back here for the final talk at 4 p.m. See you then. After the final talk, there will be a closed adjudication session. So if you do come back for that talk, I'm going to have to ask you to leave right afterwards, but we'll get there when we get there.
Hello? Hello? Yes? Yeah? Okay, good. Thank you. So look at the whiteboard or scratch paper of a computer scientist or mathematician, and you'll likely see a variety of diagrams, by which I mean schematic representations of structured objects. But as soon as you look at their screens, diagrams become much rarer, and the diagrammatic representations that are most natural to work with are often absent, or take a lot of effort to produce as custom visualizations on top of existing programming and theorem proving environments. So in this talk, I'm going to first address the question of why does this gap exist? And I think it's because existing systems can't meet the practical needs of these interactive exploratory environments. But an approach that I am seeking to develop in my research, which is compositional diagramming, can, and I'll show you how. And just as a teaser, compositional diagramming is when a diagram is formed as the composition of sub-diagrams mirroring the compositional structure of the object being represented. Here it's a tree. And I hope to develop a better understanding of how compositional diagramming works through the lens of programming languages and formal methods to build a useful diagramming system. So what is diagramming? As I mentioned, a diagram is a schematic representation of a structured object, and schematic means it uses basic shapes and visual principles like grouping or color. And diagramming is the act of producing such a visualization from such an object. Diagramming is not statistical graphing or plotting. However, there are some similarities. When you write, say, a matplotlib script to produce a graph, you might think you're writing a script to produce that one graph, but what you're actually writing is a function that converts data in some expected format into a graph of that format, and as you change the data, the graph will change. In the same way, diagramming is when you specify a function for converting objects in your domain to visual representations. This distinguishes diagramming from drawing, where there is no underlying object, or there is, but only in your head. Still, drawing languages can range from simple to sophisticated, but they're still intended to produce a single drawing or serve as a target language for other tools. Here I have examples from PostScript, which is a pretty low-level language where you specify coordinates and instructions, or you can have higher-level languages like Bluefish for composing drawings from more basic parts. So I talked about diagramming. What is this practical part? What makes a diagramming system practical? And broadly, we claim that an ideal system would make it low cost to specify a diagrammatic representation that the user can immediately start using. And specifically, there are three main features that enable that. Canonicity, continuity, and specification idioms. And this comes from some work at HATRA, which was a workshop at SPLASH 2 years ago, where we asked, we were inspired by how textual notation systems and proof assistance work, and what can we learn from their success. So by canonicity, we mean that equivalent objects have equal representations. Now, to illustrate this property and how a system might fail to ensure it, I'm going to use an example from GraphViz. And this is not to dunk on GraphViz. I mean, it's a great tool. It's meant for visualizing arbitrary graphs and has a lot of controls and knobs for different kinds of graphs. And it's also meant for doing this at scale, so it's unfair to nitpick these single small instances of graphs that GraphViz produces. However, it's a widely used tool, and I'm going to use it as a critique of constraint-based or these global non-compositional approaches to drawing diagrams in general. All right, so in this process diagram, there's two processes. There's a process that goes from A0 to A3 and forms a loop, and then there's a straight line one from B0 to B3, and then there are some crossing edges between the two. And this is part of what the spec for this graph was in the source. And then I thought, okay, well, this seems a bit redundant. Like, I could simplify it by just moving that A3 to before that A0 and it should produce the same graph, right? But in reality, what GraphViz produces is a different graph entirely. It rearranges the process A0 to A3 to rotate it by one, and then the alignment is off. And actually, if you look at it carefully, the alignment was always off with the B's. And this is because we never told GraphViz the structural information that we care about, such that, you know, A's and B's are processes that we want to be vertically aligned and keep that order fixed while we change other parts of the diagram. And in many cases, it's actually cumbersome to encode this information in a way that a tool like GraphViz can understand. An ideal diagramming system would make it easy to specify which differences matter for the visualization and which don't, hence equivalence in quotes. The next property I'm going to talk about is continuity, by which I mean incremental evolution is easy to follow. So again, the same graph and another part of the spec where you have these extra edges that go between the A's and B's. And I decided, okay, I'll add a fourth one from B2 to A2. And I would expect that the arrow just shows up between B2 and A2. But in reality, the graph that Graphs produces with this simple transformation is, again, completely misaligned. Again, and this is not, I'm not critiquing Graphs specifically. I'm just saying that when you have a non-compositional approach to diagramming, these sorts of problems are inevitable. An ideal diagramming system would have good defaults for continuity, such as using incremental graph layout, but also make it easier to specify how incremental changes are supposed to be visualized, which is especially important for stepwise exploration of proofs and programs. I've said a couple of times that the system should make it easy to specify something. Another way to say this is that the specification language should have idioms for common practical concerns. One common one is how do you fit in limited screen space? You can wrap, which is trading one axis for another. You can fold, which is to sacrifice completeness to save space. You can pack your diagram tighter together, which might sacrifice clarity. And there might be other ways, other trade-offs. Another common trade-off is composition. So even in this simple diagram with labeled nodes in a tree, I'm composing the problem of wrapping text inside the label with perhaps wrapping the tree itself on the outside. I might want to specify visual styling, which is important for my domain in order to make these graphs look good, and many other properties. To paraphrase Alan Kay, simple things should be easy to specify, and complex things should still be possible to specify. But with existing systems, you can either use a domain-specific tool that makes it simple to do a narrow range of things really well, or you implement your whole custom wrapping and styling with a lot of effort, and there's no middle ground. All right, so I've told you about why I think this gap exists, and I think it's because existing systems can't meet the practical needs of programming into improving environments. Compositional diagramming can, I claim. Compositional diagramming is when a diagram is formed as the composition of subdiagrams mirroring the compositional structure of the object being represented. Take an example. Here's a tree, and to produce a tree diagram from this object, we would start with the leaf A, which is a circle with the label A, the leaf B, which is a circle with the label B, and I put them side by side, and now I see that they're both contained in a node. So for the node, I draw the parent node, and then I connect it to its children. And I repeat this process recursively, following the recursive structure of the tree, and I get the whole tree diagram. Now, I can't manipulate pixels directly, right? There's something more going on. Let's take a closer look. When I say that the leaf A, when I say that our system turned the leaf into the circle, really it turned it into this term in some sort of slightly lower level language, where I have a circle with a label and some ports, and ports is the interface for connections with other diagrams, in this case the location of the center. And that's all that the outside of this diagram needs to know. Similarly for B, it's another circle, and then when I see the node, the parent node, the system first horizontally concatenates the two together, and the ports of this concatenation are the concatenation of the two individual ports, and then there are some spacing and alignment properties. Then I vertically concatenate that with the parent node on top, and whose ports are now just the one at the top, and finally it connects the parent ports to each of the children. In other words, what I just described is compiling objects in this format, the tree, to a higher level drawing language, which may be further compiled to a lower level drawing language like SVG, which is finally executed to produce the equivalent of a binary, might be a rendering on your screen. And this compilation step, using a compositional diagramming system, is exactly specifying that compilation step. I claim that composition lets users control canonicity because users are specifying a diagramming function. They can control what objects are treated as equivalent under what assumptions about the output parameters, like available space. So for instance, suppose instead of trees, I switched to a tree map representation where hierarchy is represented as containment. But if only containment matters, then the order is not relevant. The two squares could be swapped, or if there are more than two, they could be in any order as long as the inner space is filled for this representation. Now, if I give this diagram more vertical space, I can give it the freedom to change how its inside components are laid out if it doesn't matter to me, just to make better use of available space. I'm choosing to trade off, I'm choosing to allow it the flexibility because I view those two structures as equivalent. And so this representation might be better able to adapt to weird sizes. Composition also makes continuity natural. So suppose I started with this tree and I replaced the leaf C by another subtree, which is a node with 2 leaves, C and D. I would just have to replace, because it's compositional, the diagramming function can decide whether and how a change in a subcomponent should affect unrelated parts to minimize unrelated changes. In this case, the unrelated parts weren't affected at all, only the C and D part was changed. In fact, if I undo that step, maybe node C should stay where it was, instead of coming back in tighter. Lastly, compositional diagramming also naturally supports many of the idioms I mentioned before. So for instance, instead of composing bounding boxes, I could compose compositions of rectangles with finer granularity to keep better track of where my objects are and be able to pack them tighter together to match, to fit a target width. Other idioms like wrapping also fit neatly into a compositional approach. And note that here, actually, only the top level tree has wrapped and the inside trees are still using the full tree representation. Okay, so I told you a little bit about compositional diagramming, but is this approach powerful enough to draw the sorts of things we want to draw? So far I showed you trees and tree maps, and from my original slide, well, those two are trees. That's kind of a degenerate tree with some extra annotations. Those two were tree maps, and the rest seem a bit further out of reach. Turns out that there's another class of graphs called series parallel graphs that comes up in various domains like electrical circuits or syntax diagrams. And it's kind of a generalization of trees, where trees are graphs of tree with 1 and SP graphs are tree with 2. Now, since you can't draw these as trees or tree maps, we decided to try building a new layout algorithm, still following the compositional approach to see what we could do with it. So this is a deep dive into a class of diagrams called railroad diagrams that are schematic visualizations commonly used for formal grammars and command languages. So these examples come from a variety of domains. Those two are from the world of Pascal back in the day. And there's a bunch of more modern ones from software manuals and specifications. But despite being so widespread and intuitive, all the ones above were laid out by hand. Now, what do I mean by laid out? There are a number of interesting decisions when you draw a railroad diagram. One of the most interesting ones is that there are two-dimensional drawings, sure, but they still have a linear reading order, left to right, top to bottom. So for this, for instance, this diagram represents a sequence of an open brace and then either just a white space and then a closing brace, or a loop of white space string, white space colon value, separated by commas as many times as you want, followed by the closing brace. So I read that left to right, top to bottom, as I said. And moreover, inner components can independently wrap following that linear reading order, like the circled bit above. So this makes laying out a railroad diagram what I call a 1.5-dimensional layout problem. It's somewhere between just straight one-dimensional layout and full use of two-dimensional space. Other interesting layout decisions include, I'm going to use this example from SQLite. The schema name component and the module argument component are kind of semantically in the same, syntactically in the same position, right? There's optionally you do nothing or you do the inside of that option. But why is the schema name on top but the module argument part on the bottom? Or how come one of them seems to enter from the top and exit on the side, whereas the other one enters and exits from the side? Or why are the line breaks where they are? How do we choose to put them there? In general, there are many ways to lay out the same diagram, same being semantically equivalent. And existing approaches to drawing railroad diagrams fall into 3 categories. First, you have layout DSLs, where each decision is manually specified by the user. For instance, creating a stack with 3 elements for the 3 wrapped lines, or specifying how those optional components are to be drawn by using different keywords to say, I want it on top or on the bottom. Still, the DSL often constrains the space of possible outputs to not have all the niceties we saw earlier, like that merged edge coming in from the top. A second approach is grammar translation tools, where a grammar, here JavaScript regular expression, is turned into a railroad diagram with some automatic decisions from the tool. But these tools often have an even more restricted range of outputs, producing diagrams that are more complicated than they need to be, like in that box, or performing no wrapping at all, or giving the users no control over alignment and visual style. All those decisions are already just made and fixed by the tool. The third category is, of course, specifying the diagram in a low-level drawing language, and it's not diagramming at all. It's completely separated from the object that it used to be. But as I was saying before, in this trade-off space of tools, the middle ground doesn't exist. An automatic diagramming tool that meets practical needs while still being able to reproduce a reasonable range of what people can draw by hand. Our approach was, of course, to treat it as a compilation problem. So we have a source language, which is this language of diagrams, and it has tokens and sequences and disjunctions and loops. And our target language is a language of layouts that have more layout-specific details like widths and directions. Now, these extra details have to line up to make a sensible diagram. For instance, here the L2 has to be in the opposite direction as L1 because it's in the loop part. In other words, layouts have to be well-formed. Luckily, we managed to make the well-formedness rules fit on one slide. Now we can define what laying out a railroad diagram means. It means just the same as any other compiler correctness. You're converting a diagram to a layout such that the decompilation of the layout back to a diagram are equivalent and the layout is well-formed. Next, we implemented a compiler that follows the specification and is well-suited for practical use. So there are 3 steps in our compiler, which is vertically aligning the components of the diagram, wrapping components across rows, and horizontally justifying the distribution of space. Each step corresponds to some of the well-formedness and correctness properties I mentioned above. Further, wrapping is the only step that has to be phrased as an optimization problem, and we found that composing local wrapping decisions for each component was enough to reproduce practical layouts. We didn't have to do any global non-compositional reasoning. The alignment and justification settings I showed earlier are also just direct specifications, also local and compositional. As an example of how our compositional approach enables canonicity, here's a layout produced by our compiler. There's a 3-way choice on the bottom between the primary key unique stuff, check, and foreign key, etc. Disjunctions are binary. Disjunctions are the blue pluses. So there are actually 3 ways to express that. There are 2 ways to express the 3-way disjunction. I've associated them one way on the slide right now, but if I reassociate that term, it doesn't matter. We want them to produce the same diagram. As for continuity, suppose I wanted to replace the expression part with making it optional. So I add a disjunction with one branch that's optional and the other branch that's what it used to be before. Watch what happens to the diagram. There's plenty more I could say about this work. I'll be happy to chat afterwards. You can check out our preprint about it. The code is available on GitHub, and there's also an online playground you can actually play with this tool in. All right, so I talked about compositional diagramming, including some previous work and ongoing work. Now I want to talk about the future, mostly. I want to conclude by outlining a few directions of research that I think will help me build a useful diagramming system, and I'd be happy to hear your ideas about them at the end or chat afterwards. The first is working towards a diagramming specification language. I think that most diagrams that we use in programming and theory improving contexts can be seen as and drawn as a core compositional structure with some extra edges on top. Trees and tree maps weren't quite enough because then I had to work on these railroad diagrams separately. But if we also have a series parallel graph layout, is that enough? Or do we need more primitives? This is something I'm still thinking about. Beyond these cores, I've talked about specification idioms that would make diagramming more practical, such as compositional packing, or viewing wrapping and folding as these local, composed, combinatorial optimization problems. But so far, I've only looked at self-similar diagrams, where each diagram is recursively composed of parts that are just like itself. And I kind of have a sense of what primitives or what interfaces you need to be able to get this problem to work out. What about when I'm composing different diagramming domains? So what sort of primitives do I need for those? And going further out on a limb, I spoke about continuity and how being able to visualize transitions between steps as you explore a program or proof is important. How do we animate those transitions? How do we use the structural information that we have about rewriting rules or steps in a program to actually display those in a continuous way? And there might be other practical considerations I haven't thought about yet. A different line of research I'm interested in exploring is railroad diagrams can represent the control flow of some programs. So for instance, this might be a diagram to represent just a conditional. This one might represent a loop. But it could also represent this recursive program where I say, if the condition is true, then you go straight out and you do T, otherwise you do E and then you recurse. And the recursive call here is in the tail position, which is why I can draw it as a loop. Which programs exactly can I represent the control flow using railroad diagrams? On a different note, pre-printing code is a problem where formal approaches have been particularly fruitful in programming languages. Can 3D printing be encoded as a railroad diagram layout problem? Or what can I learn from existing fruitful approaches to 3D printing and adapt them to how I do railroad wrapping? So to recap, I think diagrams are rare in our programming and theory improving environments because existing techniques can't meet practical needs. But an approach that I am trying to develop, which is compositional diagramming, I claim can meet those needs. And I aim to use programming languages, formal methods, inspired perspective, and techniques to build a useful diagramming system for the working computer scientist, programmer, and mathematician. Thank you.
Thank you so much. So now we go to the questions from the panel.
Yeah, this is really neat work. So one thing that I'm thinking about is, yeah, can you take a railroad diagram and mix it up with tree diagrams? You sort of thinking of this as a potential future workflow. What exactly happens when you interface between those two?
Right. So one common thing that any diagrammatic representation has to do is, for instance, I have limited screen space and I have to fit within that screen space to be usable. And different representations might have different ways of doing that. Like for a tree, wrapping is a bit less natural than for a railroad diagram where you just can actually just use rows. So maybe there's a higher penalty for wrapping a tree versus wrapping a railroad diagram. So the interface could be in terms of penalties. The interface could also be in terms of how many, some sort of measure of how many decisions I have to take. Like if I want to wrap just one sequence, that's maybe one instance of wrapping, versus if I have to wrap my tree at multiple levels of hierarchy to get it to fit, that counts as worse. So there's, it's a pretty intricate combinatorial problem, I think. But my claim is that we approach it the same way we approach similar combinatorial problems for compilers when we're targeting a low-level language where there's multiple ways to express things with different trade-offs between memory and time and so on.
So there's a few little things. One, in no particular order. Have you heard of a diagramming slash language work called Penrose?
Yes, I have, yeah.
Okay, so you have looked.
Mm-hmm.
So Jonathan Aldrich is here, so you can probably talk to him.
I briefly saw him before, yeah.
No, talk to him. He's a nice guy.
Yeah. I've talked to him before about Penrose too, actually, yeah.
So that's good. With your tool, is it the feasibility or the expressivity that you see as your main goal when you create it? Is it like how usable it is for proper assistant user or whoever to understand more about what is happening? Or how much can you express maybe with this language, like checking which one of those is more important to you?
I think, okay, if you really make me pick, I think it's usability, right? Because if it is a tool that doesn't do basic things like fit within screen space, it is not going to end up being actually used. People are going to find it impractical to use.
Perfect. Now that you've chosen that path, how are you going to evaluate it? In usability studies?
Potentially in the future using usability studies, but the neat thing about doing diagramming for programming and theory improving is that I can eat my own dog food, right? Like I am a programmer and I am in a lab full of people who use proof assistance and programming all the time. So developing representations for things I actually, or my colleagues actually work with is a great way to start. I don't think I have to jump into user studies right away before I have a tool that's ready for that. So for instance, one ongoing project with a colleague is we're working on separation logic visualizations that are often present in like whiteboard explanations or like, you know, paper sketches, but are hard to produce in a proof assistant.
Final question, because you focus on the semantics for what you actually express with diagrams, what properties can you not capture, for instance?
I'm not sure I understand the question. Yeah.
Given, you've shown in one slide the semantics of the kind of properties of diagrams that you can calculate depending on whether they're fixed or whether they're going to be compositional, what things can you not capture using a self-partial language?
I think diagrams where the desirable properties are not a priori compositional are of course difficult to treat from a compositional approach. And like that sounds kind of obvious, but a good example is if I'm really just dealing with graphs, right? I don't have any underlying structure on graphs. I'm trying to draw a map of a metro system or something. Like maybe there is some structure there, but really it's a graph with connections. And I'm not targeting that, I think. Yeah.
So what I love about this is there are lots of pictures. I really like the idea of looking at pictures seriously and thinking about, okay, what can we do to better support these? That's fantastic. If you're an old fart like me, then you get asked to review grant proposals. And lots of grant proposals are something like, if we only had anti-gravity, it would be great because we could move things around more quickly and so on. And you go that and yeah, but what is your evidence? You know, then say, give me lots of money, I'll give you anti-gravity. And you sort of say, well, what's the evidence that you can get to anti-gravity? So you fell foul of that a bit. I think you've got a great problem. Obviously, it would be highly valuable if you solved it. Not so clear that you can solve it. The evidence that you can solve it is lacking. The one piece of evidence you gave is, look, I can do railroad diagrams. I think that was great. I think that's exactly the way to approach this. You didn't say this very much, but I think the right way to do is pick some special cases, like trees and railroad diagrams, and show you can do those. And then once you can do those, then for the next bit of work after your PhD, you start to generalize them, or maybe somebody else, you inspire somebody else to do a PhD. Right? This could just start a huge body of really useful work. So, but for the railroad diagrams, you gave all these properties at the beginning. Do your railroad diagrams even achieve that? You didn't say.
So I tried to address that in the slides where I talked about, let me see if I can get back there. In these slides, these are, maybe I didn't emphasize it quite enough. These are things that our layout tool actually achieves. So for instance, it actually doesn't matter if you reassociate your disjunctions back and forth. The diagram, the output layout doesn't change. And same for continuity. I mean, when I change small parts of my input expression, the diagram is indeed easy to follow across those incremental changes.
What's your evidence for that?
The evidence is on the screen. I mean, you look at the diagram before. That's one example. So if you're interested in more examples, I would encourage you to play with our online playground, which you can play around with a bunch of these little demos and see what it works.
So my feedback to you is that's insufficient.
Mm-hmm.
And right, one of your answers to Alex's question is, oh, well, I can just try it out myself. So that's, I mean, it's great for you to try it out yourself. You'll learn a lot doing that. I don't discourage that. But that is insufficient evidence that the system is good, because the evidence amounts to, oh, I tried it and I liked it. And you're kind of biased. So that's not very strong evidence. What Alex suggested, doing empirical studies, I recommend that to you.
Mm-hmm.
That would be a great way to provide good evidence. There are probably lots of interesting ways to provide good evidence, but just I tried it and I liked it is a bit weak. And in fact, as programming language designers, we used to do, I tried it and I liked it. And we were moving towards using empirical techniques. Just for the field as a whole, I want to really encourage people to do it for that. But especially for what you're looking at, I think you'd value
Yeah.
benefit by looking at that technique greatly. So pick special cases to look at, do empirical evaluation is my advice to you. But I think it's a great problem.
Yeah, and just to respond to that, I'm completely for doing empirical evaluations. It's just that I feel that some of these tools, or let me rephrase that. I think an empirical evaluation would be most valuable for me if I already like the tool I'm working with. So for me, I see it as
Using it as a first filter is great.
yeah.
Yes.
And so I definitely think that it's a direction to explore. And the second thing is there's a second way that I would like to empirically evaluate these tools, which is, can I reproduce what people already do by hand? Because what people already do by hand is probably a good approximation of what they would like to be able to do with a computer. And that...
One contribution can be, here's a database of inputs and diagrams, and anybody can use that to test their own system.
Right.
That's a great thing to produce.
Right.
Yes.
And so there is some initial work on evaluating against hand-drawn layouts in the preprint I mentioned. But I completely take your point. I agree with you.
So I
I think I'm close enough already. And part of the reason I asked this question is to get everyone in the audience thinking about, oh, but where does that fall short? Because if you have examples of where this is actually an insufficient technique, I would love to hear about it. But so far, for many things I look at, I often think, oh, well, that's kind of just a tree, or that's kind of just a railroad diagram.
This may be the kind of situation where going further on empirical studies with people outside your immediate circle would be kind of unrealistic.
Yeah. Mm-hmm.
Any other questions, either from the, we have one question from the audience.
Yes.
You know what I'm going to ask. Have you thought about string diagrams?
Yes, thank you for that question. I have thought about string diagrams, and actually, let's see. Well, I think on the face of it, drawing a string diagram is very much like a tree map layout, right? You have these boxes, and they kind of compose horizontally and vertically. While I think that's enough to actually produce the visualization to begin with, I see a main obstacle there as when you do reasoning on on string diagrams, you want to also be able to maybe animate or somehow indicate those transitions, and you want to not have to think about the association order of how things are horizontally and vertically composed when you're doing string diagrams. So, which is why I think, well, so the visual problem might be solved with tree map layouts, but the problem of actually using them in an incremental way is something that I still think is an open question.
Right, yeah. And second question, are you thinking about integrating your things with any existing, because you started talking about like proofs, and this is like a separate, like I'm assuming your system exists separately, right?
Yeah.
Have you thought about kind of integrating it with existing tools?
Sure. So like writing, for instance, a VS Code plugin, or like something that replaces the rock goal buffer with visualization would be great. But I also think it's mostly implementation work that is most valuable after I have a working like diagramming system. But yes, I do plan to do that.
Thank you. Very cool.
Okay, thank you, Andrew. Okay, so with that, we have reached the end of all of our talks. Thank you to all of the speakers. Now what I need to do This is the award. We went right up to the wire pretty much talking. But, of course, there is one person we have to select for the John Placidus Award. And without further ado, the 2025 winner of the John Placidus Award is Amanda Shu. So Amanda, please come up. We are going to convey to you, on behalf of our SIG Plan representative.
Because I'm SIG Plan executive. This is the award on behalf of SIG Plan. Congratulations.
Yes. Could we also get a shot with the whole committee?
The phone microphone is right
Yes.
there, and we want to actually the
Photo with just the two of you with the phone, and then we'll just do quick shots with a professional camera lens. I would also like to get a photo with all of the presenters, if that's okay, so just so we're clear.
thank you. And then what are the
Yes,
photos you
all
want?
of
You
the
hold it
presenters.
from now on, so that you take it all with you. So thank you.
Yes. Yeah, come on, all of the committee members.
So now
We're going
all the
to
judges.
yeah.
Okay.
Maybe use a folder. Yeah, sure.
Just look for appropriate things.
Okay, great. Now for the
And
main camera.
the proper camera.
I think nowadays iPhone takes bigger. Okay, now could we get one with all of the presenters? Yes.
Participants for new module.
So, Amanda, maybe if you go in the middle, and can we get people round?
Yeah, oh.
Let's do 2 rows. Can we get the oh, that's not going to work. We'll just block. It'll work.
That's okay, this will work.
Yeah.
We'll just whatever, it's fine.
Yeah.
Come here, it's fine.
Are we all visible?
If you can see the camera, the camera can see you.
Not true. You can step out a bit.
Me?
Yes.
Okay.
Just let me check for a while. Okay, 1, 2, 3.
Oh, well.
And one more with the
One
professional
more.
camera.
Yeah.